the question, and questions may be solvable, but I'm not. I mean,
Confident enough.
yeah, I'm not feeling that much of satisfaction to like what like till week 5. I felt I'm very confident. Like I can
Right.
solve any question, but in week
Right.
6, yeah, sir.
Okay,
So
fine.
can you please, sir, provide some source that where I can?
So one thing is definitely you can follow the book which we are uploaded. We have
Okay,
uploaded in the
okay,
portal, right? So that is basically we all together have written to make a summarize, to make the summarize of all the weeks, all the linear algebra portion at least. So you can follow that book if you can enough. If you get enough time to read that, I
okay,
think that will
okay,
be
sir.
enough. So and
So
anyway,
you're
we
saying
will
about
discuss.
books?
We will try to discuss some topics.
So, to begin with, I just wanted to ask that is this
Yeah.
session going to be uploaded on YouTube since you're recording?
Yeah, so I will record it. So maybe tomorrow morning I can upload it
No
because
issues,
it
no
takes
issues.
time
That is
for
not a
processing.
problem. Just wanted to ensure that is it going to be uploaded so that we
Yeah,
can
it
be
will be
rest
uploaded.
assured.
It will be uploaded.
Yeah.
Yeah, it will be
Thank you.
uploaded. Okay, so let's start with the quiz question first. Okay, so I will ask you how you solve it, and then I will write some portion of the solution maybe. So is this visible to all of you?
Yes.
Yes, sir. It is
Yes,
visible.
please.
Okay.
Yes, sir.
So if I take the first question, there are a matrix is given for some real number A, and we have to answer the following question. So a power 4 is beta, a power 4 identity. Then what is the value of beta? Right? So what we should do for this?
We should multiply A for 4 times and then is equal to beta A is to 4 into identity matrix of order 2.
Right.
Then we will get the value minus.
Right.
Yes, sir.
So
It's all about calculation only.
yeah, it is nothing else, right? So if I take A as this, what was my A
Minus
minus
A.
A. A minus A. So one thing I can do, I can take A out, right? I can write it as this. Okay. So basically, it will easier my calculation somehow because the portion which is outside, I can take the square of it, and this is basically product of this matrix, right? And what is this? This portion will come as 0, and this is 2. This is minus 2, and this is again 0, right? So till this portion, is it okay?
Yes, sir.
Yes,
Fine. Again, I can to easier my calculation, I can take outside 2, and I can write 0, 1, minus 1, 0. Correct? So what is a power 4? I have to multiply these 2 times, a square square. Right? So this is 4, a power 4, and this is 0, 1, minus 1, 0. 0, 1, minus 1, 0. So if I do this, so this is minus 1, this is 0, this is 0, and this is again minus 1. So basically it is minus of identity matrix, take outside that. So this is 1, 0, 0, 1. So minus 4, a power 4 identity. So what will be the value of beta? Beta is minus 4, right? So somehow I can little bit minimize my calculation if possible, right? So this is the first one. What about the second one? Find the value of a plus lambda for which determinant of a minus lambda is 0. Anyone have solved
Sir,
has solved it?
uh,
Yeah,
yes, sir. Uh,
yeah.
Sir, firstly, you should form that matrix A minus lambda I,
A minus
and
lambda
then
I. Okay, let me
yes,
write it. What is a minus lambda I? So a was this, right?
yes, sir.
And minus lambda I means so this. So I can write it as 0, this a minus lambda, a minus a, and a minus lambda. Now what is
Yes.
the determinant of it?
A minus lambda the whole square plus a square.
A square, and this is given as 0,
Yes,
right?
sir. Yes, sir. And then you can just, I mean, a
Now
square,
what we should do?
that will become a square minus 2a lambda
Hmm.
plus lambda square plus a square.
Hmm. Hmm. Then?
So then, so can you please continue with that? I mean,
Then,
Okay,
sir,
but do we really need that? This is square of two real numbers, right?
yes, sir. Sir, after solving
So,
that, so here in the question, it's mentioned that we should treat a as a variable.
right, no issues there. But here it is
Then,
also written that lambda is a real number
yes,
and
sir.
also
To
a
get,
is a real number which to begin with, right?
yes, sir. To get
So both of
lambda,
them are real number.
yes,
This
sir.
one and
To
this one.
get the real value for lambda, we should in that equation, it's a quadratic equation. So we can
Right.
make the d, which is b
Discriminant to
square
be
minus, yes,
right,
sir, b square minus 4ac should be greater than equal to 0.
right.
And then somewhere you will get lambda in the form of minus sign. I mean minus lambda square.
Hmm.
Then that will become that should be greater than equal to 0, which is for any number except 0,
It must be 0,
it is
right?
not possible. Yeah. So the
Correct,
only value it can take is 0, and you will
correct,
get lambda 0, and then you can put lambda in that equation.
correct, correct.
From where you can get
So
the
the
value of
process you
a
are
as
telling is
0.
correct, but that is really lengthy, right? We really don't need that. Here we have two real number of which squares sum of their squares are 0, right? So each of them should be 0, correct?
Yes. Yes,
That
sir.
I can
Yes, sir.
calculate
Yeah.
from here directly. So a must be 0 because this is 0, and a minus lambda must be 0, which implies a should be equal to lambda, and a is already 0. So what the lambda value should be? It is also 0. Now what is a plus lambda? This is 0, correct? We don't
Yes,
really
sir.
have to
Yeah.
bother about the quadratic equations. Clear? Is it clear to everyone? Anyone has
Yes,
done
sir.
in this way?
So-
Anyone
No,
here
sir.
who has done this problem like how I have written? No?
Sir, how come a plus lambda also becomes 0, sir?
Because a
Can
and
you
lambda both
explain?
are 0, no?
Okay.
So what is a plus
We
lambda?
are
0 plus
assuming
0.
a as 0, or the equation gives the answer itself as 0, sir. A is equal to
I am
0.
not assuming anything. This what
Okay.
this gives. This equation, what this equation gives. This is sum of two real numbers, right?
Yes, sir.
And when I have, suppose I have an equation like this, x square plus y square equal to 0. Can I say something about x and y?
No, sir.
X is equal to
No?
y is equal to 0.
Both of them should be 0, right? Because they are
Okay.
real number. Either they, I mean, both of them must be greater than equal to 0. Now, if I have sum of two positive real number giving me 0, what the values can be? They must be 0, right? Otherwise, it is
Okay,
not
sir.
possible because
Okay,
none of
sir.
them can be negative. So both of them is 0. That is giving us a equal to 0 and a minus lambda as 0.
No, sir. If we put a plus lambda is equal to, okay, then lambda doesn't become minus a. So, okay, again it becomes 0. So it does, minus doesn't have any impact. Okay, sir. Okay.
Clear? Yeah.
Yes, sir. Yes, sir.
So this is basically, if you just this strikes in your mind, if this strikes in your mind, then it is very small problem, not a lengthy problem at all. So this is done, I think. Anyone has any doubt in question number 1? What we have discussed till now?
No, sir.
yes, sir.
Oh, great. What about the second question? If there is a square matrix A such that a square plus a is 0, the determinant must be either 0 or minus 1. Is it true or false?
Either 0 or plus 1. It can be minus 1, I think.
I mean, it can be also, right? So any okay, whatever this statement means, if it is false, you have to give me a counter example. Is there any counter example? can you give me a matrix A for which this equation satisfies, but determinant A is neither 0 nor -1? Can you give me a matrix like that? No? We have done it in activity question, if you remember. So,
1 0
right.
minus
Take
1.
minus identity matrix. Right? What about A square of it?
1 0 0.
So it is 1 0 0 1. Correct? Correct? A square is identity matrix,
Yes,
right?
sir. Yes, sir.
So A
Yes.
square plus A, what that is?
So zero matrix.
Zero
Zero,
matrix.
Zero
right?
matrix.
So condition is satisfied. Now what about determinant of A?
1.
1. So I have an example for which this equation is satisfied, A square plus A equal to 0, but determinant A is neither 0 nor -1. Right? So we have an example. So this statement is not true, clearly. Okay? Any doubt?
Yes, sir. No, sir.
Okay.
No, sir.
Okay. What about the second one? U is the solution of the system of linear equation Ax equal to C. C is the solution of the system of linear equation Ax equal to B. Then U is the solution of the system linear equation Ax squared x equal to B. Basically, we have to put what it is written. If you just write it down, it will be done. Right? So U is the solution of Ax equal to C. This is given, and C is the solution of Ax equal to B. So what we have? So this is option 1. This is option 2. So Ax equal to C. So U is the solution of that. So we have A equal to C. Correct? Now C is the solution of Ax equal to B. So what should I write? AC equal to B. Right? So instead of, in place of C, I can substitute AU. So what I am getting? A square U equal to B. So U is the solution of the equation A square x equal to B. U is the solution of it. Clear?
Yes, sir.
Any doubt?
No.
Anyone has any doubt?
No, sir.
No. Okay.
No, sir.
You can ask me wherever you have some doubt, you can ask me directly, okay? No issue. Okay, now if B is the diagonal matrix of order 3, then AB minus BA equal to 0 for all square matrix A of order 3. Is this a true statement?
No.
Why?
We can take general diagonal matrix A and then we will do it. Then it will not be 0.
Right. If in place of B, diagonal matrix, if we have scalar matrix, will then the statement be true? Instead of diagonal matrix, we have scalar matrix. Then
Yes, sir. It will be true because we can take that scalar out and make it identity
Correct.
matrix.
correct. So for scalar, all the diagonal positions should be equal, right? So it is some C into identity matrix. If that is the case, then this equation will be satisfied. But diagonal matrix, it is not necessary that all the diagonal elements will be equal. So it is not necessary that AB minus BA equal to 0. You can take any diagonal matrix and test it. So you can write it like this. Suppose you take your diagonal matrix side 1, 2, 3. Right? So if you take AB, and whatever matrix A you take, any matrix, okay, A, B, C, D, E, F, G, H, I. What is AB? What is AB? A, B, C, D, E, F, G, H, I. This is 1, 0, 0, 0, 2, 0, 0, 0, 3. What is AB? Can someone tell me? No? What is the
A.
first? A.
2B,
Ah.
2B
3C,
and 3C.
3C, right. Then
B, uh, 2E,
B, 2E, and
3A.
3F.
3F.
So basically multiply this with the diagonals. So G,
2H
2H,
and 3I.
3I. Correct. Right? So I have written down this method. What about BA? Now you can see where the difference is coming. So this is 0, 0, 0, 3. And if I write this A, B, C, D, E, F, G, H, I. So if I do it by left side, what I will get? This is A, this is B, this is C.
C.
Now here, these will be 2D, right? 2E and 2F. So it will be column wise. So 3G, 3H, 3I. So can you see the difference? These two matrices are not equal, right? So AB minus BA will not be 0. Correct? Is that okay, everyone?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, great. So option 3 is also done. What about option 4? A into adjoint of A is 3 identity. Then determinant of adjoint A must be 9. Is it correct?
Yes.
Yes, sir, it is
Why?
correct.
Why?
Because adjoint of A can be written as
Hmm.
in A inverse is equal to 1 upon that formula. Then we
Can you
can
tell me the formula? What that is?
Sir,
A
adjoint
inverse
of A can
A
be
inverse
written
is
as
equal to 1 upon determinant of A into adjoint of
Correct. Anyone want to approach it in some other way? Without using the formula, anyone wants to do it?
Sir, we can take determinant of adjoint of A is equal to determinant of A की power n minus 1.
Determinant of A power
Yes.
n minus 1, right? If A is a n cross n
Yes, sir.
matrix. So this is basically a derivation from this formula only. Right? So this we can derive directly from this formula. If you don't know this formula, if you don't remember this formula, then also it's okay. You at least remember this one, right? A inverse. How we can find A inverse? We take the adjoint, we divided it by determinant, right? That is an algorithm we know. So what if we take determinant on both sides? What I will get? So this is a constant, right? So determinant of 1 by determinant of A, which is a constant, and adjoint of A. And this is what I am getting. Now, what about determinant of A inverse? This is 1 by delta. Right? And this will come outside. Now, it is a suppose it is a 3 cross 3 matrix or n cross n matrix. Then it will come out as power n. Right? And then determinant of adjoint of A. Right? So if I take this adjoint of A, if I take this in this side, what I will get? Determinant of A power n by determinant of A. So this is determinant of A power n minus 1. Clear? So this is how we derive the formula. Right? Now here what is given? A into adjoint of A is 3 into identity. A into adjoint of A is 3 into identity. So if I take determinant on both sides, what I will get? Correct? This is what I am getting.
Yes, sir.
And we know that A is a 3 cross 3 matrix. So n is 3 here. So determinant of A into some other matrix, A into B. So this is det A det B. Right? We can break it up. And what is the determinant of this one?
9.
27.
Is it
27.
No, 27. 27.
3 cube.
because this is a 3
3
cross
cube.
3 matrix.
Yeah,
3
20.
cross 3 matrix. Right? So it is 27. And so determinant of A. And what about this one?
9.
No, I mean, what we should do now? What we have to find? We have to find determinant of adjoint of A, right? So I can write it as determinant of A 3 minus 1, right? As we have calculated. So this is 2. So eventually it is determinant of A whole cube. It's 27. So what about determinant of A? It's 3. Because we are talking about real number, so it is 3. So determinant of adjoint then 3 minus 1. That is 3 square, that is 9. Clear? Anyone has any doubt in this?
No, sir. Sir, in the first question, can we take this approach by taking determinant of both the side? In the first one, A minus A, to find the value of beta.
You want to take the determinant on both the side.
Yes, sir.
Yeah, you can take that, but even okay, you can do that. I think. Yeah.
Sir, because I am getting two value of beta from this +4 and -4.
That is the issue because I mean here as a matrix I am writing, right? But determinant will become a polynomial type of thing that may have more than one value because that will be a 4th degree equation.
So that means, sir, we cannot apply this type of method in this.
No, it is better to do in terms of matrix.
Okay, sir.
What you are getting if you do determinant?
As say
I will let
beta
you know.
square is equal to 16, so beta can be plus or -4.
That is the issue because there are 4 values, but because here is identity matrix, so that will be determined by the thing, whether it is plus or minus.
Okay, sir.
Right? That's why determinant may not give you the
Sir,
exact value.
Sir, have you
That will give
this-
you equation, but it will not give the exact value.
Sir,
Yeah.
that's why I made mistake in this question.
Got it. Yeah. So, any doubt till question number 2? Anyone has any doubt?
No, sir.
Sir, I have
Yeah.
doubt in this option 2. That
Option 2.
because in exam I took some random example and tried and it did not satisfy.
But it must be, right? Because I have a proof of that.
No, it did not satisfy.
What is meant by so basically what is meant by a solution, right? If I say use a solution of this system of linear equation, then what does it mean? It means that this will be the value, right? AU should be equal to C, correct? Then only U will be a solution. That is what I have written here. Then if I have an equation like this and I know C is a solution, what I know? AC must be equal to C. That is what I have written here. Right? Now, just put the value of C here. What is C? C is AU. That will be one solution, right? So A square U equal to B. So one solution of this A square X equal to B must be U because you satisfy this equation. There can be other solution also. Right? I am not denying that. There are no more solutions. U is the only solution. That is not what the question claims. Question claims U is a solution.
Okay,
Right?
sir, understood.
There can be infinitely many solutions. But U must be a solution because it satisfies the equation. Got it? Yeah. Okay. Great. So this is done, right? What about question number 3? So here I have defined an addition. Whatever 2 vector you take, you just add it up, it will give you 0, 0. And whatever scalar multiplication you do, it will give you 0, 0. So everything is branching to 0. That is the point. Now for this, whether 0 element exists, that is the first one. First statement
No,
is saying that.
sir.
Second statement is saying the commutativity of scalar and
The first statement is wrong.
like that. So first statement is wrong. Why?
Sir, I think zero
Because
element
there is-
is not unique here.
there is no element which will give you back x1, x and y.
Right. So what was the definition of zero element? It is already written there. So I take x comma y. There should be something for which I should get back x comma y. Now, if x and y both are, at least one of them are non-zero, that is x comma y is not 0 comma 0, then there are no element here which will give me the same element back, right? Because whatever element I will write here, the addition dictates that it is 0 comma 0. So it should not be equal to x comma y. But we have started with. Is it clear? Unless x and y both are 0 comma 0. Correct? So there are no zero element for this addition. Is it clear?
Yes, sir.
I think all of you are saying the same thing.
Yes, sir. Clear.
So still. Okay, so this is the first thing. So 1 will not be satisfied. What I should write here, enter the serial number, addition and scalar multiplication. Not true. So 1 is not true. What about remaining 3? Are those true?
Yes, sir.
Yes, sir. All are true.
Yes,
All
sir.
are true.
That's
Because
all.
whatever you do on left hand side and right hand side, you will get 0 and 0, right? 0 comma 0. Whatever you do. So this is the process. Anyone has any doubt in this?
Sir, for the fourth one, for the scalar multiplication, what we are telling. So c into xy when it is giving 0 comma 0, that means in this case it is a special case where only c has to be 0 only.
No. What I have defined, it's true for all xy and all c. Whatever c you take, I have defined the scalar multiplication like that. Okay. For any real number c, I have defined c into x comma y is 0 comma 0.
Right.
Whatever c you take, that's how I have defined it.
Okay.
Right? The definition of addition and scalar multiplication is on our hand, right?
Right.
Now I have given you 4 axioms which you have to check. So definitely the first is not true, as you have already checked, because 0 is not there, 0 element is not there. But what about the last option? AB into V. So AB is a scalar, right? Whatever your V is, if you do the scalar multiplication, it will give you 0 comma 0. That's how scalar multiplication is defined here, right?
Right.
Now what about BV? B is a scalar, V is any x comma y. If you do this, what you will get? 0 comma 0.
0
Right?
comma 0.
Again, A into 0 comma 0, according to the same scalar multiplication, it will give you 0 comma 0. So fourth option is also correct. 4 axiom holds. Right?
Okay.
Yeah,
Got
that is what I am saying. So 2, 3, 4 will be trivially hold because everything is 0 comma 0 on left and on right. Okay, so only first statement 1 does not hold here. Correct? Right. Any doubt in question number 3?
No, sir.
No, sir.
No, sir.
Okay, great. Now the first one, W, x comma y comma z, and x, y, z are real, and x square plus z square is 0. Now,
Yeah, sir. The
first of
basis is a singleton set for this. So the dimension is
Yes, sir. 0 A 0.
right. So x square plus, so this is again the same thing. Subspace 1, or what I have written, subspace or subset here. Subset. I should write subset. So subset 1, W is basically written as xyz, such that xyz are from real and x square plus z square is 0. So what does it mean? It means that x and z must be 0. Right? Again, sum of square of two reals. So this is nothing but 0, y, 0. So only one thing is free here. Right? So if I want a basis, you can give me a basis of W as 0, 1, 0. So dimension of this is 1. Clear?
yes, sir.
What about subset 2? X equal to Z. Right?
This is
So
dimension
let me write
2.
it. Why?
The basis has
X
two
comma
elements.
y comma x will be the span.
Yeah.
Right. So this is this thing. So I can write it like x, y, x. Right? I can replace z with x. So only two free variables are there. So basis of w I can take as 1, 0, 1 and 0, 1, 0. So there are two elements in the basis. So dimension of w is 2. Clear? So
Yes,
this
sir.
type of problem
Yes,
we have
sir.
solved before exam, right? Subset 3. What was that? Now there are two equations, right? So x equal to y plus z and x plus z equal to y. What should I do now? So what are the two equations? Let me see again. X equal to y plus z, x equal to y plus z, and what was the
X
next
plus
one?
Z equal
X
to
plus
Y.
Z equal to
X
Y.
plus z equal to y. Right. So two equations. So we know how to solve this type of thing, right? We can, let's see what are the solution. X minus y plus z equal to 0 and x minus y plus z. So this is I have written something wrong.
Sir, x minus y minus z.
Sir, you can take the value of x from equation 1 and put in equation 2. It
That
will
also I
Z
can do,
equal to
but
0.
I prefer to do it in this form because that will directly give me algorithm will give me my answer, right?
Oh, okay.
So
Okay.
this is what it is. So this is R2 minus R1 I can do 0. This is also 0, right? And this is 2, correct? If I have done it correctly.
Yes, sir.
Yeah. So yeah, now again, I actually don't know. So what I am getting from here, so x minus y minus z equals 0 and 2z is 0. So z must be 0, that I have got already from here. And what about if z is 0, then x minus y is 0, so x equal to y.
X equal to
This
Y.
is so what my w is basically. W is becoming x 0.
0.
And x is real number. So how many free variables are there? It is clear from here on. 1, right?
Only one.
So basis of w, if I want to write one basis, I can write it like this. So dimension of w is 1. Clear?
Yes, sir.
Okay, great. So this is also 1. What about the last one? So subset 4.
So please show them. No, the question.
Yeah.
Question.
This one, right? Question I have to see. It's this one. Yeah. So x, y, z, x plus 1 minus y plus 1 plus z equal to 0.
This is the same
And
equation.
someone
X
tell me
minus y
what-
plus z equals 0.
Yeah, you get the same result. X plus
Same thing, right?
X plus Z equal to
So
Y.
x plus 1.
So
this
it will again
minus
be
z
2.
is-
The dimension will be 2.
So it is not same. I mean similar type but not same. X plus z
Yes,
equal to y.
one equation is same, but another one is different.
Another is different. So two equation I am getting. So here plus 1, this will cancel out. That is one thing. So these two equation I am getting. So this is basically, these two are exactly same equation, right? This is what you are telling about, right?
Yes, sir.
Yeah. So basically we have only one equation because second equation does not actually do anything.
Yeah. So it's 2.
And so there are two free variables. I can replace z in terms of x and y. So what I can do is x, y, and I can write z as y minus x. And x, y becomes y. So two free variables are there, right? So basis, if I want a basis of w, I can write a basis like this. So dimension of w is 2. Clear?
Yes.
Anyone has any doubt till this question? Question number 4?
No, sir.
No, right? So this is done. What about question number 5? I have two subspaces of R3, W1 and W2, right? XY and X plus Y, XY 0. Two subspaces. And the operations are usual one, addition and scalar multiplication. Usual addition and usual scalar multiplication. Now I have to find which represent W1 intersection W2, and then I have some questions along that line. So first of all, how we should find W1 intersection W2?
Sir, will it be x comma y and then x plus y equal to 0? That be the intersection.
Sir, W1 intersection W2 will be x minus x 0.
X minus x 0. Why minus x?
Because in the
Because
first
x plus
equation,
y, yes, x
that
plus y
was
is
given as
equal to 0.
right, sir.
Sir, I will say xy is 0.
No,
You
so
are
that's
saying
what
x, y,
x
0.
comma y comma x plus y equal to 0. So that gives x equal to minus 1.
So basically, how you should approach this? So let me write this W1 and W2. So W1 is x, y, and x plus y, right? Where x, y belongs to R. And what about W2? It is x, y 0, right? That x, y belongs to R2. So this is the z coordinate for both the two. If I want to write it in terms of x, y, z, what is the equation here? This is basically z equal to x plus y, no? Correct? This is the condition I am getting, x plus y equal to z, right? So basically this is the plane. This is the plane passing through origin which satisfies this equation. Right? Anyone has any doubt in this? So I have mentioned that whatever the subspace of R3 it is, it must be a plane passing through origin or a straight line passing through origin, right? Or it is whole R3 or 0. So these 4 types of subspaces are there. So this is a plane passing through origin which is satisfied by the equation x plus y minus z equal to 0. Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. What about W2? Can you write W2 similarly? So this was written. So what about this? Z equal to 0. So this is the plane just z equal to 0. So if I write z equal to 0, this plane. Now intersection mean, what is the intersection of these two planes? So I have two planes. This is one plane and this is another plane, right? What is the intersection of these two planes? What does it mean? This
When
means
z is 0.
no, first of all, this means the solution of this system of linear equation, is not it? The solution of this system of linear equation, right? That is the intersection, correct? Because this will, all the points x, y, z, we satisfy both the equation. That is what we need, right? So if we put z equal to 0 and as it has to satisfy the first equation also, so x should be minus 1 or y should be minus x, whatever side you take, right?
Yes, sir.
Yeah. So I write y equal to minus x because that is the conventionally we should take, and z equal to 0. So the intersection is basically the set of solution of these two equations, that is x minus x 0, right? When x belongs to R. So this is my subspace W1 intersection W2. Is it clear to everyone?
Yes, sir.
Yeah. This is one important type of question, right? What is the intersection of this? So this is the intersection. Now, in the option, which option are correct? Span of which options are correct?
Sir, option 2, option 3.
Why option 3 is clear,
Yes, sir.
right? 1 minus 1 0, because if we put
Yes,
x
sir,
equal to
that
1
is a
here, I get
basis.
1 minus 1 0. Now many of you can put option 3 as correct option and leave that. But you can also see that if we add any linear dependence set to that, the span will not change, right? So you have to check whether some set contains that or not. So this is basically minus of 1 minus 1 0. So I am adding a linearly dependent vector to that set. The span does not change. The span will be W1 intersection W2. So both option 2 and option 3 are correct. Is it clear?
Yes, sir.
Yes, sir.
Because
Yes,
both
sir.
of these, both option 2 and option 3, the dimension of the span is basically 1. And that is same as, and that space is basically same as W1 intersection W2. But if you see the option 1, these two are linearly independent, right? So dimension will be 2. So it cannot be W1 intersection W2. Similarly for the last one. Even it does not satisfy W1 intersection W2, the equation x minus x0. So it cannot happen, right? So option 2 and option 3 both are correct options. Now what about dimension of W1 intersection W2? We have already seen it is 1, right?
1.
Right. Now what about W1 union W2? Is that a vector space?
No, sir.
No, sir, it won't.
Why?
Sir,
Why?
because you can take any element, take one element from W1 and take another element from W2. And if you add those, it won't fall under, I mean, it's not, it will
not
it will
necessary.
not be closer.
It will not be closed under addition. No scalar multiplication.
Sir,
So
can
can
I
you-
prove it?
Yeah, definitely. So take one element from W1. Give me any element from W1. Can you give me an element from W1?
2,
One, two. Suppose I
1
can take
comma 1 comma 2.
Right? 1, 2. Okay. Now take another element from W2. Give me another element from W2.
1 comma
W2.
530.
I should not write equal, belongs to. So this is XY0, right? So someone has said 530. Right. Now if I add these two, what I am getting?
642.
642. Does it belong to W1?
No, sir.
No, right? Because if I add 6 and 4, I am not getting 2. Right? Because if it has to belongs to W1, then the x coordinate plus y coordinate should be equal to z coordinate. Z should be equal to x plus y, but it is not the case. So it does not belong to W1. So it does not belong to W1. Does it belong to W2? No.
No,
right?
sir.
Because the last coordinate is not 0. So it is not belong to W2. So it does not belong to W1 union W2. Because it neither belongs to W1 nor belongs to W2. Clear?
Yes.
But as this one belongs to W1, it belongs to W1 union W2. This belongs to W2, that implies it belongs to W1 union W2. If it is a vector space, then sum of these two must belong to W1 union W2, but it is not the case. Clear? So, W1 union W2 is not a vector space. Clear?
Sir, just
Yeah.
a small question. Whenever the case of union comes, can we safely take the assumption that it does not constitute a vector
No,
space?
I mean W1, so you can check this one. W1 union W2 is not a vector subspace. Not a vector subspace. If basically it will be a vector subspace, let me write in this way. Is a vector subspace if and only if either this happen or this happen. If one contains another, then only it can be a vector subspace, otherwise it cannot be. Right? So this is, I leave you to check. Basically, what is happening in this case? If W1 is a subspace of W2, then what is W1 union W2? Can anyone tell me? if W1 is subspace of W2, then
W2.
this is W2, right? Correct? Because this is my W2. W1 is sitting inside that. So the union is basically W2. And W2 is a subspace, we know. So this will be a subspace. In that case, it will be a subspace. And similarly, if W2 is subspace of W1, then what will be the union? W1. Then also it is a subspace. So only in these two cases, it will be vector subspace. Otherwise, it will not. Right? There is a proof of that. Okay? Understood?
Yes.
Oh, great. So this is, I think, no one has any problem in question number 5, right?
Yes, sir.
Okay. Yeah. So the addition in this question number 6, the addition is defined like this. Scalar multiplication is defined like this. Now, is the statement P true? Is P true?
No, sir.
Why?
P is not true.
Why?
P is false.
Sir, because inverse doesn't exist for the 0, 0 vector here, I think.
What is
And
zero,
this,
zero vector here?
Yeah, sir. The scalar multiplication,
One
I
by
think one
x-
of the axioms
1
fails
by
for the
x
zero
comma
vector.
1 by y will be the zero vector here.
Yeah.
And that will not satisfy for x1 and y1 is equal to 0.
Yes, sir, exactly.
And you have
Can
Because
you
1
repeat
by 0
what you
is
are
not
saying?
defined.
yes, sir.
Right.
And the same
But,
question I have thought
But
also in the
one
lab,
minute.
in the live
One
session.
minute. What is zero vector you are saying here? So there should be some
Sir.
vector which give you this, right? What is
1 by
zero
x
vector?
comma 1 by y. 1 by x comma 1 by y.
Yeah, sir. That's based on the scalar multiplication operation defined for this space.
No, sir, actually
Scalar
that's
multiplication is
based on the
CXCY.
addition that
Oh, sorry. It's on the
is
addition.
defined.
Addition is actually multiplication.
Yeah, sorry, sir, sorry.
So what is zero vector according to this addition?
Sir, 1 by x, 1 by
1
y.
comma x and 1 by
1
y.
comma 1.
1 comma 1, right?
Oh,
Not
yeah,
1 by
yeah.
x, 1
Zero
by y.
vector. Yes, sir. Yes, sir. Zero vector
So
will
this
be
is
1.
1 comma 1, right?
Yes, sir. The inverse vector will be 1 by x, 1 by y.
The inverse vector will be. So if I take the inverse, so what will be?
Yeah, sir. The inverse is 1 by x and 1 by y.
Inverse
Then
is
want
one
to
what is
get
the
0,
problem
0.
here? Then what is the problem you are
So
facing
it's
there?
not defined for 0, 0.
It's
0
not
comma
defined.
It
0.
says 0 and y is
0 comma
0.
0,
Yeah.
it does not have any inverse, right? That is what you are telling, right?
Yes, sir. Yes, sir.
Correct. Yeah. Fine. So this is one way we can look at it, and there are many. I mean, some of other exam will also fail.
Sir, actually, a simple one is if we put x2, y2 as 0, 0, and we will not obtain this x1, y1 again.
But it does not necessarily that 0, 0 is always the zero vector of
Okay.
vector space, right? Here 1 comma 1 is the zero vector according to this addition, right? Yeah. So it is fine. The other two examples, I mean, this addition is commutative. Is this addition commutative? I mean, that
Yes,
has
sir,
nothing
it
to do
is
with the question. I
commutative.
mean,
It
question
is
you already know
commutative,
is,
sir.
but I am still asking. It's commutative. What about
Yes, sir, it
associativity?
is true. It is also associative. Yeah.
It is associative. It also has 0,
Yes, sir.
right?
Yes,
As
sir.
you can see, 1 comma 1 will act as zero vector. But the problem arises that zero vector, I mean 0 comma 0, not zero vector. 0 comma 0 does not have a inverse. Correct?
Yes,
This
sir.
is where we are facing the issue first. Correct. Okay, fine. What about statement Q?
Q is
Is
true,
a vector
sir.
space?
Yes, sir.
Is
It is.
Why?
Sir, sir, you can just you can make U as minus B by A B minus B by A B minus C by A W, because A is not 0. I mean AC is non-zero, so the
So either I mean, both of them must be non-zero.
Yes, sir, exactly. Then AC
Both
is
of them
not
must.
0.
Right?
But
So
what if
what?
B is 0?
That doesn't matter, no? Yeah. So let me write it. Okay. So for Q, this is okay. This is for question number 6. So 0, 0 does not have any inverse. This is why B is false. And for statement Q, what I am getting, AU, BV, CW. AU, BV, CW is 0. Right? I have to show span of UV is same as VW. UV same as span of VW. Right? AC is non-zero. This is what it is given. That means A and C both are non-zero. That we know. Right? So this is what we have. Can I divide? I mean, with C. I can write this, right? I can write. So this I can write. So W I can write in terms of this, correct?
But C is 0, then how can it be divided?
C is 0.
C is not 0 here.
AC non-zero means A and C
Okay.
must be non-zero, right?
A,
Both A and C must be non-zero, correct? Otherwise AC can be 0,
okay,
right?
okay. Right, okay.
So I can write W in terms of U and V. So basically, the span of V and W, I can replace W as a vector of U, right? By this combination. So span of these two will be same.
Sir, I have a doubt here.
Yeah.
Sir, actually what I am saying that A and C are non-zero. That is true. But there might be a case that either of B or V can be 0.
B or?
B or V can be 0. Is there a possibility?
Then what is the issue in that?
So issue is
B can
that
be
if
0.
B and V or 0, then span of U and V and span of V and W will never be same.
Why?
Sir, because suppose V is 0 and B is some constant real thing.
Correct.
And V is 0. But here the case is if AB plus CW has to be 0 and A and B are non-zero, then U and V cannot be same. They need to be different.
So
Sir, how span of UV will be equal to span of
So
VW?
suppose V is 0. You are saying V can be 0, right?
Okay,
Suppose
yes,
V
sir.
is 0. Although there are no condition on UVW, what I am saying,
Yeah.
there are condition on given as only ABC, that is
Yes,
enough.
ABC.
Okay.
Yes.
Okay, let's assume V is 0. Then what
Okay,
is
sir.
span of UV?
Sir, span of UV will be span of U.
Span of U only, right?
Yes, sir.
Okay. And what is span of VW?
It will be span of W.
Span of W, correct. Now if V is 0, what is the equation I have given you?
It will be AU plus CW equal to 0.
Right?
Okay. Yes, sir.
Then?
But but if we look at the above condition, then span of UV will be equal to span of VW only if span of U will be span of W. In the case when V is 0.
So
right?
in this case, this U and W are linearly dependent. That you are getting, right?
Yes, sir. But sir, that
Yes,
means
this
they
one
will not be
span
equal
is same,
to.
na?
Sir, but
No, they are
listen,
linearly dependent. So span will be same, no?
sir, they are linearly independent.
Dependent.
Sir,
Dependent, non-zero, non-zero.
yes, sir. Yes, sir.
So they are linearly dependent. So the span will be same.
Sir, but how, sir, V and W will be same, sir?
V and W, I am not saying same. What is span of UV? This is span of U, right?
Sir,
Is this step clear at least? 1 minute, let me finish. Okay. Is
Yes,
this
sir,
step
that-
clear?
Yes, sir, that is clear.
Span of VW is span of W. This step is clear. Now what about AU? So I am getting AU plus CW equal to 0, right?
Yes,
AC
sir.
both are non-zero. So U
Yes,
and
sir.
W are linearly independent, right? Linearly dependent.
Yes, sir.
Linearly dependent, right?
Sir,
So span of
independent
U and
will
span
be,
of
sir.
W. No,
Yes, sir. Yes, sir.
why?
Dependent. Sorry. Yes, dependent.
Then span will be same, no? Because W is a scalar multiple of U and U is
Yes.
scalar multiple of W, right?
Right, sir.
I
Right.
can write like this, right?
Right, right, sir.
So span will be same, no? I can replace W here by minus AC U.
Okay. Yes, sir.
Correct?
Yes. Yes, correct.
Similarly, for B also takes 0, you will get the same thing. Because this is what we are doing. Here, no condition on B and V are required in our proof, right?
Yes, sir. Correct. Correct. Right. Correct.
So I think you have misunderstood here because it is dependent, not independent.
Yes,
AC
sir.
non-zero
Actually,
means
I misunderstood the term dependent over there
right.
because time was less. So
Right.
yes, right.
Now
It
is it
right.
clear? Now it is clear,
Yes.
right?
Yes, it is clear, sir.
Yeah, great. Yeah, so Q is true and P is false, right? Statement 2 is correct. Anyone has any doubt in this?
Sir, please explain that second.
So that is what I was doing till now, right? So if AC is non-zero, then both A and C are non-zero, right? Is it clear? The A and C cannot be zero.
Yes.
Both of them, right? Because if one of them is zero, then AC must be zero. So that is not the case. Now, so just take, suppose C is non-zero. So I can divide with C, right? Because 1 by C is valid in that case. So divide the equation by C. So I can write W as minus ACU. So I should take minus here inside. Plus minus BCV, correct? Now, what is span of G and W? Span of G and W means, so this is something XV plus YW, something like this for X and Y. And I can replace the vector W by this equation, right? So I am getting some combination of V and U. That is span of UV, correct? Is it clear?
No, no.
Okay. What is span of G and W? Can you tell me what is span of V and W? What is span of G and W? Because I have two vectors. What is this set? What is span of V and W?
AB plus BW.
So A, instead of A, I am writing X because A, B are already used. So I am writing X and Y, right? This is the span,
Yes.
correct?
Yes.
You have no doubt in this?
No.
Correct?
No.
Okay. And this is also clear to you that I can write W like this using the equation?
Yes.
Correct? Okay, great. So, if I just write XV plus Y in terms of W, I am replacing this by minus A by CU minus B by CV. Correct? This I can write. XY belongs to R. Right? I just replace W with U and V as a combination of U and V. So what I am getting eventually? I am getting, this is XV and this is, so XV and minus BY by CV plus minus AY by CU. Correct? So I am getting a combination of U and V, as you can see here, because I have replaced W in terms of U and V. Right? So now, whatever, which vector are in the span of V and W, they can be written as a linear combination of V and U. Right?
Yes.
So this is span of V, correct? Suppose
Yes.
I have vector
Okay.
here. I have vector here. Suppose vector V tilde. Okay, this vector. Suppose V tilde is a linear combination of V and W. So XV plus YW. I can write V tilde as a linear combination of V and U also, because this can be replaced by this X minus VY by CV plus minus ay by c u. Same v tilde I can write in terms of v and u as a combination of v and u. So v tilde will belong to span of uv. Similarly, converse you can check. You can take any vector from here and divide the linear combination what it is there, the equation, divide it by a. You can get in terms of v and w. That is also you can get. Right? Is it clear? No? You can ask me if it is not clear.
Okay,
I will
okay.
explain again. Is it clear or no?
Oh, yeah, sir.
Yes.
Please, sir, explain it just once again from starting.
Oh,
Just explain. No, sir, not
Fine,
need to write it, but what you had written over.
no, better. It will be better if I write it once. No issue. So I have this, right?
Yes, sir.
AC is non-zero. That means
Yes, sir.
A and C both are non-zero.
Yes, sir.
Correct?
Yes, sir.
Okay. Now, first of all, I am taking a vector v tilde from span of V and W. Suppose I am taking a vector from here. So, what does it mean? V tilde can be a linear combination of this. Correct?
Yes, sir. Yes, sir.
I want to show that this v tilde can be a linear combination
Yes.
of u and v.
Yes.
That is my first issue. So what I will do, I will write, so this is AU minus VV. Now C is non-zero, so I can divide with C. Right? So I replace W in terms of U and V. That is what I am doing. So Y minus ACU minus V by C V. So this I can break it down. Correct? So
Yes,
I
sir.
can write it x minus by by cv minus ay by c u. So you can see that now it is a linear combination of v and u, these two vectors. Correct?
Yes, sir.
So v tilde is now in span of
V and U. Yeah.
u and v. So I have chosen a vector v tilde from span of vw. I have written it as a linear combination of v and u. So it is now in span of uv. So this
Yes, sir.
portion is clear, right? This is subset of this.
Yes, sir.
Correct? Now if you want to do the reverse, so I have chosen a vector v prime from span of uv. So v prime is some combination of u and v, right? And I have this equation. Now I want to replace u in terms of w. That is also I can do because a is also not zero, right? Correct? This I can do. So x u I can replace by this. So what I am getting is right. So v prime now is a linear combination of v and w.
Yes, sir.
So v prime is now in span of v and w. So I have chosen a vector v prime from span of uv. I have written it in span of vw. So
Sir, there is
span of uv.
YW, then how can you get common V? YW and CX upon AW. Then you have written.
This is yv, yv. This is yv.
Okay.
Okay. So span of uv. Now I have chosen a vector from here. I have written it in span of vw. So this is my second thing, and the first thing was the converse. Vw is subset of this. So by 1 and 2, these two are equal.
Yes, sir.
Yeah.
Sir, means we have to do this whole process to say that.
No, actually you don't have. It is really clear, but you were unable to understood. That's why I have written the whole proof. But it is not really
Then-
necessary. Once you know that this W can be replaced by U and V, then it is clear, no? Whatever vector you can write as linear combination of VW, that can be written as the linear combination of UV. From this step only, it is clear. Because this should come in your mind. Right? Whatever vector I can write as a linear combination of VW, as W can be written as linear combination of U and V, then those vector can be written as linear combination of U and V. Correct?
Oh, yes.
Right. So you don't have to do this proof actually in the exam. But you wanted to see this, that's why I have written it. I mean, this proof is quite trivial. I mean, there is nothing in the proof. This is just calculation here. And you don't need the proof. The point is, span of VW means what? All those vectors which can be written as linear combination of V and W. Correct?
Yes.
So, sir,
Now W can be
span of U and V will be W.
What does it mean? Span of UV is one vector. No, that is not how I am saying. I am saying I can write W as a linear combination of U and V. Right?
Yes, yes.
So, span of VW means what? Span of VW means all those vectors which can be written as linear combination of V and W. Now, W can be also written as linear combination of U and V. So, whatever vector which I can write as a linear combination of V and W, those vector I can write as a linear combination of U and V, because W is a linear combination of U and V. I can replace W with U and V.
Oh, yeah. Yes, sir. Yes.
Is it clear?
Yes, sir.
This is what it is. The question is, you don't have to do all this calculation actually. Okay? Understood, everyone?
Yes, sir. Yes, sir.
Yeah. Now, who was asking this? There are some other people who are asking for this problem, right? Is it clear to you now?
Yes, yes.
Yeah. Okay, great. Just take a look and think for 1-2 minutes. I think it will be clear to you again. So this is also done, right? Now this big question, comprehension type question. Right? So basically some process is given with the probability
Sir, sorry to
from
interrupt.
state 1 to state 2 there. Yeah.
Are both the sets covered in this document?
No, this is only set 1 and set 2 is a just the digit will be different maybe.
Means it would be shuffled one.
Not shuffled one, digit can be different also.
Okay.
Some digit can be
Because
different.
this is the paper what I got, but in second paper as well, similar questions are there. So that's why I asked.
Exactly same question will be there, but digit will be different in some places. Right? Not even in all the questions. Yeah. So this is the diagram. This is basically saying the probability of going from state 1 to state 2 is half. Probability of going from state 1 to state 3 directly is half. Now, there is no probability of going from state 2 to state 1. That's why it is 0. But there is a probability from going from state 3 to state 1. That probability is half. And probability of going from state 2 to state 3 is 1. Probability of going from state 3 to state 2 is half. So I can write this as this probability matrix: 0, half, half, 0, 0, 1, half, half, 0. So once I know the initial state, the probability of the system in the initial state, if I multiply it with, I will get the next state. The probability of the next state that I will get if I multiply P with X. Right? This is what the comprehension tells us. Right? I have to take the transpose because I am applying from the left side. So that is what it is written here. Pt xn minus 1 is Pt xn. So basically what here it is written, if I want to write it like this, Pt xn minus 1 is xn. So that means Pt, suppose I1, this is x naught, then it is x1. Similarly, Pt x1, what it will be? It is x2. And it will go like this. Right? If I multiply the initial state, this is suppose the initial state, I take the probability matrix. So this will give me the second state probability, the next step. And similarly, go on. We can go on till xn. Right? This is what is given in the comprehension. Now, suppose that p equal to 2, that is the distribution vector x2, this is given. Can we conclude something about x0 and x1? This is the question. Really, the question is.
Sir,
Yeah.
sir, I mean that x vector. I mean, what that represents actually the entries of that.
The distribution vector, how these states are distributed. What is the probability of state 1 and state 2 and state 3 at a particular time?
What is the probability?
How they are distributed, how this state 1, state 2 and state 3 are distributed in this system. Right? Suppose you are having a chemical reaction. Right? Now suppose these are compounds, some compounds, compound 1, compound 2 and compound 3. So I am giving this in a context of chemical reaction. Now, so how the compounds are distributed? Right? What percentage of compound 1 is there, what percentage of compound 2 is there, and what percentage of compound 3 is there. It is like that. Is it clear?
Oh, okay.
So this situation can be applied in many situations. I mean, not only chemistry, this can be applied in physics, this can be applied in computer science language, anything, anywhere it can be applied. This is famous, this is known as some connection with Markov chain, basically, from there it is. So this is one of the applications what we have done till now. Right? So you know x2, you have to talk about x0 and x1. Can we do that? That is the first question. So x2 is 1 by 3, half, and 2 by 3. This is the distribution vector. x2 is, so you know this vector, 1 by 3, half, 2 by 3. Half, 2 by 3. This is x2. So do we know what is x1? So basically, what is your pt? So let me write p. P is 0, half, half, and then 0, 0, 1, half of 0. 0, 0, 1, half, half, 0. Right? This is p is given. Now, what is pt? The transpose of it. So I get this p. I want to know what is x1. So x1 is basically how it is written with the subscript. So x11, x12, x13. So these are just coordinates. And this is my x2. So basically, what is the solution of the system? This is what we wanted to know. Clear?
Yes, sir.
Is it clear to everyone that what we are trying to find? Yeah.
So this question was there with different values, and are we supposed to
definitely
do
set to
all the things because Roy-Club form reducing it takes some time. Because there were
will not take
15
some time.
questions.
That is what. No, that is not. So even if it is a defined value will be like similar, right? So I can show you if there are some defined values. Set 2, right? I should have it somewhere here. This is your set 2. Yeah. See? Even P is exactly same in set 2. Right? Only this value is also same. So basically this question is same in both the sets. Right?
Okay, so
Okay. So this is half x13. This is 1 by 3. So you know how to solve it. Should I do it or you can do the solve? Right? This is x1. So if I want to write the equation, this is like this 1 3, this is half. This is the system of equation you are trying to find the solution. This is the system of equation. So you can do the row operations here, and you can get a solution of x1 1, x1 2, x1 3. Right? Anyone has done the solution? Anyone has done the solution?
Not here, sir. Actually, it was done in paper.
Okay, but I mean, did it take
No,
much time
not actually.
to solve it?
No, sir.
No, right? It
Yeah.
should not be, right? Yeah. So definitely, I mean, one easier way to solve that this determinant, see the determinant of this matrix, this is non-zero. So there are exactly one solution. So, and either as you can do the row echelon form, you can take this upstairs and do the row echelon form, you can do it. You can directly solve from here. You know x13 is basically 2y3. x13 is basically 2y3. This is directly, you can get it from here. Put it in the second equation, you will get x11. So this is half x11 plus half 2y3. So this is 1/3. And this is half. So you get half x11 as 1/2 minus 1/3. So this is 6, 3 minus 2, 1, 1/6. So x11 is basically your 1/3. Okay. And similarly, put it here and you will get x12. x12 is half minus 1/6. Again, it is what? 6, 3 minus 1 over 1/3. So 1/3, 1/3, 2/3. This is what your x1 is. Similarly, you can put it again in the first equation, you will get x0. And one more thing which is important in this problem is basically you can put pt. So x1 is x2 and pt x0 is your x1. You can put the value of x1 here. So basically pt x0, pt square x0 is your x2. This is what you get, right? So if you want to find x0 directly, just take the multiplication of pt 2 times, the square of pt, and solve with that system of equation. Then you can get directly x0. Okay. So this is what the first problem is. Anyone has any doubt in this? And infinitely many vectors means basically I am asking whether it has infinitely many solution or not. The system
So,
has infinitely many solution. Yeah.
so can't we find the solution for x0 and x1 by taking inverse, like PT inverse?
You can find. Definitely. Why not?
So I've solved like the same method by finding the inverse of PT inverse, and then finding out the xn minus 1.
But that will take more time than this process, right?
And I've got
But you
different
can do.
answer, but I've got the different x0 and different x1 answer.
Then you do it wrong. You did it wrong. I mean, definitely that's the case, right? You have made some calculation mistake or something. So that's why it is better to do Gauss elimination whenever you are in this type of situation. Okay.
Okay, sir.
So,
Sir, what you said that infinitely
huh?
what you said about infinitely many vectors.
Whether
That
there are
also.
infinitely many solutions or not, that is what I am saying.
But here we are getting one vector for x0. That's why not that.
So there are no possibility of infinitely many solutions, right? Yeah. So see whether this. So basically, we have to do Gauss elimination. I mean, this is nothing. This is the system of linear equation. You have to solve it. The exactly same thing, right? You have got this system of linear equation. You have to solve it, right? And see whether there are infinitely many solution, no solution, or unique solution. Right? And what is the solution? If there is a unique solution, what is the solution? You have to find it. Correct? Is it okay or should I have to solve it?
No, sir, got it.
No, sir, it's okay.
Okay, no, you can
Yes,
solve
sir,
it,
I
right?
think
Yeah.
Yeah. And what about the second one? Similarly, again, x1 is given here. Now, this is a good question. Now, for this x1, can we know what x naught is? That is the first thing. Now, when you solve for x naught, so here, see, option 2 is correct. What does it mean? The system initially is in state 3. That means the solution which you will get is basically 0, 0, 1. That will be a solution for x naught. And what does it mean? State 1 and 3 are in 0, right? So this does not exist, right? So the system initially is in state 3 because at third coordinate you have 1 probability. Is it clear what I am saying?
no, sir.
No, sir.
So if
Please
you
No,
repeat.
sir, not clear. Can you please explain it a bit more?
so suppose this is my P, right? 0, 0, half, half, 0, half, half, 1, 0. So I don't know what my x naught is. But x1 I know it is given as half, half, 0. Half, half, 0. Right? This is what I am seeing. Now I am seeing, see, when you solve it, you will get the solution as 0, 0, 1. Now if you check it, this is the solution. You can verify it at once. So if you do this product, this will be half. And this product, this will be half. And this will be 0. So this is your x1 which is given. And this one. So this is a solution. You have to solve it, but this will be a solution. This is your x naught. X naught is 0, 0, 1. So what is x naught of 1? This is the state 1. This is 0. This has probability 0. X naught of 2. This has probability 0. And x naught of 3. This has probability 1. So in which state your x naught belongs? Everything is in the state 3, right? State 1 is 0. There is nothing in state 1. There is nothing in state 2. But everything is state 3. Is it clear?
Yes, sir.
That is what I was saying. Okay? Is it clear to everyone?
Sir, means if
It's clear
probability
now,
is-
sir, but then to think of all these things and make this question work in examination might have taken a lot of time, seriously.
Is it? I mean, you have to just find a solution of x naught, right? And once you know the x naught, then if you understand this concept clearly, right, then no other option can be, right, and can be correct. The system is initially in state 3 means what? At third position, you have 1, coordinate is 1, right? I mean, for concluding that this option 2 is correct, you don't have to do any calculation. What you have to do, just solve the system of linear equation. That is what you have to do.
Sir, we have to find
And
x0.
all the other things should be conceptualized, right? It is not testing your calculation skill or anything. Correct?
Yes, sir. Okay.
Yes, sir.
Okay. And what about the last one? Both p and p square have same reduced Western form.
Yes,
So
it is
if
Yes,
you do
sir.
this p and p square, you
Yes.
know what your q is, what your p square is. If you do the row reduction, you have already done the row reduction of these two because you have to solve for x0 and x1. So we assume that you have already done the row reduction in the first problem. So definitely you can conclude something from here. P is already in reduced Western form. Clearly this is not correct because the form which we have given, that is not reduced Western form. P square is lambda p. Again, we have assumed that p square you have already found for solving the earlier equation. So you know that that is not equal to lambda p. And p square is already in reduced form. We have, again, you know what p square is, so you can directly mark that this is not the case. Right? So if you have solved the first question, then the last question is a corollary of, you can directly put what is the correct option in the last question. Right? So basically, in these three questions, you have to solve only A and B. C is the byproduct of that. Right?
Yes, sir.
Okay. Anyone has any doubt, you can ask me still. Right? So this quiz question, the solution of quiz question, is it clear to all of you at least?
Yes,
I
sir.
agree that it may take 1 hour 15 minutes, maybe it may take, if you use the longer method and all this, but not more than that it should take. Last question was quite a new question to all of you, but it must be the case. In every quiz, you can expect a question like that. Every quiz or in MSEM also.
Sir, but
Yeah. Yeah, Aditya, tell me.
sir, in distribution matrix, sir, there is the probability of distribution matrix should add up to one, right? Question it
Your
doesn't
voice is
adds up
breaking.
to
I am
one.
not getting it properly. I think your voice is breaking. I think your voice is breaking. I am not
Now,
getting you properly. Yeah.
there's one doubt on chat.
Okay. What is the doubt?
Megha has asked it. X distribution matrix should add up to 1. So that one. The last third comment.
No, we are not saying in that sense. Okay. So that's why this is, I am not saying in terms of, so this distribution of these three may not add up to 1. That is not the issue here. We are not considering in that sense. We are giving you a vector in
But,
which, suppose in the whole portion, I mean, suppose it is like this, 1 by 3 kg, half kg, and 2 by 3 kg in the second step. That is what we are saying. We are not saying it is the percentage inside 1 kg thing, 1 unit thing. We are not claiming that, right?
but sir, that will add 1.
So you are saying the name distribution vector is not appropriate here, right? That is what you want.
Yes, sir. Yes, sir. Right. Right, sir. So,
Yeah, that may be the
because
case. I agree to that. I am not saying this is not true. Yeah.
So because
But here I have explained it,
ambiguous.
right? But in
Yes, sir,
this
process is
comprehension, I have never claimed that. No, I am not saying even the process. So I have, in the comprehension, I have never mentioned that this distribution vector is basically the distribution vector which is in statistical sense. Right? That is not what I have claimed.
But, sir,
So I have written what.
if we add that to the compute probability, then sir, we will take statistical sense, sir. Sir, but
If suppose this is not adding up to 1 minute, suppose it is not adding up to 1, is this affecting the solution of this problem, or how we approach the solution? Is it affecting that? No, I think, right?
Sir, approaching the problem, it won't affect, but sir, the gist of the problem, sir, that numerical is wrong, sir. That's what I think.
But that is what I am saying. I am not giving you the distribution vector in that sense.
Okay, sir.
Right? Yeah.
Okay, sir.
So I agree that the nomenclature should be different. We should not mention it like distribution vector. We should coin some term. But again, that will be more confusing to all of you because you know probability matrix. So it is better to give you distribution vector. That's how it is distributed. Because otherwise, again, another term should be coined. I should explain another term that will take you some time to read again. So better than that, you know distribution vector. I just give you that term. Right? That's what I have given that time.
Yes,
yeah. Okay. So any doubt in quiz question? I think I have solved all the question, and it should not take more than 1 hour or 1 hour 15 minutes. That's what my conclusion is. Right? Anyone has any doubt in quiz question, or else should we move to the week 5-6 revision? Okay.
Week 5-6 revision, sir.
So we should move. Sir,
Okay.
there is one generic doubt, sir. Can I ask?
Yeah.
Sir,
Yeah.
sir, can't the solution of activity question be provided in the dashboard?
Then it will be really spoon feeding everything. No?
Sir,
You have solution of
I'm saying
practice, you
after
have
the
solution of dated
completion of
assignment.
week, sir. After the completion of week.
But again, why don't you solve and you create a solution for yourself? Why you
Yes.
don't do that? Why you need solution for every question in the portal?
Question of which I'm not getting the solution. And
You can ask in the discourse, you can discuss about the
yeah.
solution. In discourse, you will get a hint. Why don't
Yes,
you
sir.
do it yourself?
Yes,
Right?
sir. I'm following the same process, but I was thinking that if it is
Ah.
given, then it will be more easier.
No, actually, we don't want it like that.
Okay, sir. Yes, sir. Got it.
Yeah.
Sir,
Yeah.
sir, the due date for practice assignments, can it be extended?
Now it is on Sunday, right?
No,
Sunday or
last
midweek.
week it was on 16th and on that.
That I agree. So that will not be considered for your bonus for week 6. Okay? Because that clashed with your quiz, right?
Yeah.
Yeah. So
And
that
I
will
did
not be
cover
considered.
the content as well.
That will not be considered. That you will get an announcement for that. Okay.
Okay, sir. Thank you,
I have
sir.
already informed on the portal team. Yeah. Fine. So now let's begin with the 5 and 6 revision. So you know what null space of a matrix is, right? Can someone tell me what null space of a matrix means? Yeah, tell me.
It's the
Null space.
solution of equation AX equal to 0.
Right. So it is all those x. So suppose A is my m cross n. Then where it should belong?
Sir,
Rm or Rn?
it's Rn, sir.
Rn.
If I have variables, then it will be Rn.
Rn, right. So x in Rn such that Ax equal to 0. That was the definition of null space, right? And you know how to find the solution of it. Right? Now, then in week 6, we have come to know something about linear transformation. Right? And what was linear transformation from a vector space V to W? How we have defined it? How we have defined a linear transformation from one vector space to another vector space?
Sir, it is a function which satisfies the property of linearity.
Two properties, right? Yeah. So a diagram I have drawn earlier also. Right. So this is V1. Suppose there are two vector V2, and this is your W. So this side is my V, this is my W. So this is a mapping T, which takes, so V1 will be taken to some TV1, V2 will be taken to some TV2. Now there is an addition in this side, right? Vector space addition. So it is V1 plus V2. And there is an addition also, right? So this will be add up to TV1 plus TV2. Now this vector will map somewhere, but we expect this to be mapped to the same element here, right? So that's why the first condition is coming. V1 plus TV2 is TV1 plus V2. This is the first thing we need. We demand here. Similarly, for the scalar multiplication, we demand this CV, CD. Right? So this is the condition for linear transformation. Now, once we know the linear transformation, if I do it from Rm to Rn, right? Rm is a vector space with usual addition and scalar multiplication. Similarly, Rn is a vector space with usual addition and scalar multiplication. How it will look like? So x1 to xn, which is applying on this thing, and it will be here it will be a linear combination of all these variables basically, right? So a1 1 x1, so let me write it as sum first, then I will add it up. A1 2 x2 and this. So this is the first coordinate. I want it like this. Right? Similarly, there are n many coordinates. So all this will be a combination of linear combination of these variables. So this is n1 x1, n2 x2, and here nm xn, right? So this type of combination will be there. So basically what my point is, I can write a matrix A and I can take this as a vector x1 to xm and I will get this linear transformation, right? So any linear transformation from Rn to Rm to Rn, I can write it T of V as AV, right? Where A is a matrix. Clear? This you remember, or anyone has any doubt in this?
Yes,
Are you
sir,
there?
done, sir.
So this is this till this portion, is it clear to everyone?
So can you repeat?
Okay. So suppose start with the small example. Let's say R3 to R2. So I am saying x, y, z. So I can write it 3x plus 2y minus 5z and y plus 3z. Okay. This is a linear transformation, right?
Yes.
Yes, sir.
Now I am saying that I can represent it like this. So this is nothing but I can represent it like this, product of these two. Correct?
Yes, sir.
Sir, but here you don't check for that two conditions, and how can we quickly say that it is transformation, linear
Because
transformation?
any linear transformation will be of the form as a linear combination of these variables, right? No power should be there, no constant term should come here, or no combination, no product of these two variables should be there. If it is simple linear combination of the variables, then it must be a linear transformation, and all the linear transformation will be of this form.
No need to check that two conditions.
You can check, but it will be satisfied.
Okay.
Okay, you can check anyway. You can check. You should check all the two conditions. It will be satisfied. But my point is, if it is a linear combination of these variables, no constant terms are there, no powers are there, no product of two variables are there, 2 or 3 variables are there, then it will be a linear transformation, right? And whenever it is a linear transformation, I can write it as product of these two matrices. So basically, I can take TV as A into V, where A is this matrix. Okay.
Sir?
Yeah. Yeah.
Okay.
Sir, one clarification. When we get xyz, t of xyz, shall it mean that this 3x plus 2y minus 5z is range, and we have to equate it with x and y and z?
I am coming to the range later. Okay. No, this is not. I mean, this is not range. This is not range. That's how we don't define the range, right? I am coming to that. Okay. So till this portion, is it clear that I will get a matrix like this? Correct?
Yes.
Yes, sir.
Yeah.
You should be little bit more interactive. Okay. Otherwise, I cannot do it like this. Suppose I am giving you this linear transformation. Can you tell me what the matrix is in this case?
Sir, 1 minus
Sir,
1,
1.
1 0 1 1.
1 0.
रुको यार.
1, 1.
Right. So I can basically write it like this. This is what I am getting. Okay. So any linear transformation, I will get a matrix like this. Now, what is null space? Null space of a linear transformation.
So here how
Do you remember what was the definition of this? Because this is 0 y, right? Y coefficient is 0.
It's right.
Right? You do this product, you will get this vector.
Yes, yes, sir.
So what is that?
So null space of T, what is null space of T? It is a vector, all those vectors from V. So T is a map from V to W. Right? All those
T
vectors
of
from
V.
V for which TV is going to 0. Right? This was the definition. Right? Now, I know this T I can write is as the matrix A into V in case of Rm to Rm, and what we need really in our situations. So it is Rm to Rn. So basically, can you see a similarity here? So this is what a null space of a matrix, right? So same thing we are extending to a null space of a linear transformation, right? Whatever the null space of the matrix is, it is the null space of the linear transformation. Clear?
Yes, sir.
Is this
Yes,
okay?
sir.
You can see the definition is same because TV is same as AV. So I have just replaced it with AV. Right? Okay. So this is the definition of null space. So what I was doing, so this is my V, this is my W. There is a 0 here, there is a 0 here. All those vectors of V, which is going to 0 of W. So this is 0 of W. This is called null space of T.
Okay, sir.
Correct?
Yes, sir.
Yes, sir.
This is called null space of T. Now,
The
do you
vectors
remember that null space?
excuse me, sir.
Yeah.
The vectors from V which will give 0 in W will be the null space.
Exactly.
Oh.
Exactly. All those vectors which is going to 0. Okay. So, do you remember that null space of T is a subspace?
Yes, sir.
Yes, sir.
Right? So, if there are two vectors which are in the null space, then their addition will be inside null space, right? If these two are in null space of T, then basically TV1 plus V2, their addition is basically TV1 plus TV2, because this is a linear transformation, this is 0 plus 0 is 0. So V1 plus V2 is inside null space. Similarly, the scalar multiplication, if V is inside null space, then T of CV is same as C of TV is C into 0, then it is 0. So CV is inside null space. Clear?
Yes.
So null space is a subspace. This is clear, right? Now, so
Yes, sir.
subspace means it has a basis. There exists some basis of it, and the dimension. So it
Yes,
has a
sir.
dimension, and dimension of null space is called
Nullity.
Nullity.
nullity. Good. So this portion is at least clear, and you have a similar definition in case of matrices because they are exactly
Yes,
the same,
sir.
right? So till this portion it is clear.
Sir,
Now let's come to yeah.
sir, here null space is subspace of which V or W?
You tell me.
V.
No, let him try.
Okay. It
Can
is
you tell me?
mapping to W. It is mapping to W. So
But where
that's
null
W.
space is, can you see this diagram?
Yeah.
Where it is situated?
V.
V. So it is a subspace of V. It is inside V, right? We are taking all those vectors of V which is going to 0. So null space is inside V because it is constructed with the vectors from V.
Okay.
Correct? Oh, great. So this is one thing. Now let's come to range space. Range of T. So T is V to W. So as a mapping, what was W? W is the codomain, right?
Right.
Codomain of T.
Where the
Okay.
image is formed.
Right, exactly. A range is basically set of images. Right? Range is basically set of images. Okay. So basically, what I can write, all those basically take all the V's, all the is TV. This is your range, right? Take every element from V, take the image. Set of all the images is basically your range. Clear?
Yes, sir.
And I have proved already in my earlier session. Do you remember that range is also a range of T is also a subspace. And subspace of what? Subspace of
W.
Okay. So basically, Again, if I draw the diagram, take all the V, take the images. It can be whole W, but it may not be also whole W. So for diagram representation, I am doing it like this. This is going to 0, this portion. Here it is, my 0 vector inside W is there. So this is my range space. This is my null space.
Sir, I have a doubt.
Okay. Yeah.
So for range of T, like it is TV, such that V belongs V, should we not apply also an additional condition that TV belongs to W?
I mean, where TV can belong elsewhere. I mean, T is a map from V to W. No? So when you take TV, it must be inside W.
Okay,
Not
got it.
mentioned,
Got it.
right?
Got it.
Yeah.
Sir,
Right.
sir,
So
there
this
a doubt.
is the whole diagram.
Sir, my doubt is that, sir, every element in V will be mapped to every element in W, right?
Not to every element, to some element of W.
To some elements, okay.
Every element of V will be mapped to some element of W.
Okay, sir, okay.
Right? Every element of V will be mapped. That is sure. That is for sure.
That is
because
true,
we have to
for
cover the
being a
whole domain.
function. Yes, yes, sir.
But we don't know whether every element of W will be mapped or not. Right?
Yes, if it is mapped, then
Because
it will
when
be
that
onto.
situation arrives, then it is called on.
It will be onto.
that. Right?
Yes,
Such
sir.
a-
Okay, sir. Thank you, sir.
Right. Exactly. Okay. So range is a subspace that also I have proved in my earlier session. You can go back and take a look there in the note. Also, you can take a look. So that also has a basis. That also has a dimension. So what is the dimension of range called? This is called rank of T. Right?
Yes, sir.
Okay. Fine. Now there are some condition which is called rank-nulity theorem, which is really important here. So I will take rank-nulity theorem first, then I will come back to 1, 1 and on to mapping because there is a reason for that. So rank-nulity theorem, what it is saying, rank T plus nullity T, it is same as dimension of V. Okay. So T is a map from V to W. You remember this diagram. So dimension of this null space, dimension of this is called nullity. Dimension of this space is called rank. If I add these two, somehow I get dimension of V. We don't need the proof for now. Okay, we just need the statement of the theorem. Right? So
Sir,
rank, yeah.
is it dimension of V or dimension of W?
Dimension of V. Okay, it is dimension of V. Okay. Now, if I consider this theorem, now let's take an example. How this is working. So take this example.
But sir, in normal rank nullity, it is dimension of W. Means
No,
L.
it was never dimension of W. It was always dimension of V. Okay?
Everywhere it is mentioned
Normal,
dimension
abnormal,
of V
whatever
only.
theorem you take, it is always dimension of V. Okay? Because
Sir, in
in
your
matrix,
last
what you
session,
have-
you said it's W.
No, never. I have never said it. is
Because we are finding it from the matrix of that transformation.
Then also it is dimension of V.
Yes, sir. I am saying that because the number of columns is same as the dimension of V.
So if A has M cross N, right? So I have T Rm to Rn. Can you tell me what is the, I mean, if TV equal to AV, what is A? A is what cross what?
M cross
N cross M.
N cross M,
N
right?
cross M.
Yes.
Yes.
N cross M, correct? Now,
Sir, I don't understand that. N cross M.
is it? Okay. Let's go back to the example, what I have taken earlier. Say this one. R3 to R2. What is this A? It is
2 into 3.
2 cross 3, right?
Yes.
Right. Now, if it is 2 cross 3, then if I consider this matrix and I want rank nulliety theorem for this matrix, what was that? Rank of A plus nullity of A, what it should be?
Dimension of V.
No, just tell me the number. It is a 2 cross 3. What
3.
it should be?
3.
3, sir.
This
3.
one, right? And what was 3? It is dimension of V.
Okay.
Is it clear?
Yes, yes.
Consider the next one. This one. What is this matrix?
3 cross 2.
3 cross 2, right? If I take Rankine theorem for this matrix,
2.
2. And who was dimension of this one?
Okay.
Okay. It was always dimension of the domain. Okay.
Okay.
Clear?
Yes.
Okay, great. So we all agree that this is dimension of V, not dimension of W. And I have not said it anywhere.
Sir, that is why we write n to m to satisfy that n equal to rank plus
To
the
make the parity like that. Yeah. Right.
Okay.
Okay. Okay, fine. Now let's consider an example and dig it a little more deeper.
Shobhajit, just one clarification. Can you go back to that null space of matrix and null space of linear transformation? So here, just for clarification, in case someone has got it wrong, you cannot find the null space of the linear transformation by finding out the null space of the corresponding matrix. You cannot choose any matrix of the linear transformation.
Susmita, I will explain it later. Actually, it is only true for standard order basis.
Yeah.
Right? We get the same null
so,
space for standard order basis, and this A matrix is basically standard order basis.
Okay, fine.
So we can find null space for that. Okay.
Can you please
I will
repeat
explain.
again?
I will come to that. I will come to that. What Susmita has pointed, I will come to that. Okay, because I have not reached that far yet. Okay. Okay, fine. So let's say R3 to R2. Let's take a map. T x y z, x minus y, and say y minus z. Okay. Can you tell me what is the null space of this? What is the null space of this? Null space of T. How we should do it? Basically, all x, y, z such that T x, y, z is 0, right?
Yes, sir.
This is the null space of T we know. So basically, x, y, z such that x minus y is 0 and y minus z is 0. Correct? So basically, we have to solve this equation, right? 1 minus 1, 0, 0, 1, minus 1, right? If this is x, y, z, this is 0, 0, right? This is what we have to solve. So basically, what I was saying, if I want to write it as TV equal to AV, what is my A here? You can say this A is the same matrix, right? Correct?
Yes, sir.
Anyone has any doubt till this point?
Sir, here in matrix, you told it that in linear transformation cases we have to write column wise. Means I'm not able to interpret why row wise was written.
What I have written here, I am saying this is not the matrix representation what I am talking about. I have not reached to that point. I am just saying any linear transformation, I can write it as TV equal to AV, right? Any linear mapping, I can do that. Right? And this is how the matrix can be written. Because if you take the product of this matrix, you will get these two vectors, and this vector, right? X minus y and y minus z, correct?
Yeah.
If I take the product of these two matrices, what I get? I get x minus y, comma y minus z. Right?
Yes, sir.
This is what I am writing. Right? I am not talking about any matrix representation or anything till now. Okay? Do you agree to me on this point?
Yes.
Yes, sir, it is correct.
Okay, fine. Now, basically, we have to find the solution of this thing, right? So what I get, so this is already in row echelon form, right? Maybe not reduced, but already in row echelon form. So I can do one step basically, R1 plus R2. If I can do it, I will get 1, 0, 1, sorry, minus 1, 0, 1, minus 1, correct? So basically x minus z is 0 and y minus z is 0. So x equal to z and y equal to z. So what is the null space of this?
X.
X.
Yeah, right, x is real. Yeah, and observe that this is the null space of this matrix A. The same thing, right? This null space of T and null space of A is basically the same thing. Correct?
Yes, sir.
Because that matrix I am getting here, right? Anyone has any doubt at this point?
No, sir.
No? Right. Okay, great. Okay, so this is the null space. What is the nullity of it?
1.
1. Great. Now, can we use rank-nullity theorem to find the dimension of the range?
Yes.
Rank plus nullity was what? It is from R3 to R2.
So it will be
3,
3.
sir.
Right?
3, sir.
So rank will be?
Rank will be 2.
Rank will be 2. Now, if I ask that whether this map, this linear transformation is surjective or not, what you can say?
Sir, yes,
Surjective.
it is.
R2 it will be surjective, sir.
It is surjective, right?
Yes,
So
sir,
when
it
it
will
is
be
surjective, so if dimension of W and rank of T is same, then it is T is surjective. Correct? And in this case, it is the case. Rank T is 2 and dimension of W is also 2. So basically, codomain and range are same. That was the case, right? For a map, codomain and range should be same for surjectivity.
Sir, can we, sir,
In this
take
case,
it like... Sir, can we take it like this? If we are, sir, making transition from M to N, and if M is greater than N, then it will be surjective.
why you need to remember all this fancy stuff?
Sir,
And you don't have to actually, right?
Sir, actually, the curiosity was coming in my mind because if we are making a transition from higher dimension to lower dimension, that means every point will be mapped.
No, it is not always true. No?
Not
I
always
can
true.
give you an example. Not always.
Okay.
That's why I am saying don't remember all
Okay,
this
sir. Okay, sir.
in this way. So basically, the definition of surjectivity you know for a map, right? When the range and codomain is same. Here we know that codomain and range both are vector spaces, so they have a dimension. So their dimension should match. That means dimension of W and rank of T should match. Correct? In that case, T is surjective. Okay? This is an if and only statement. Okay? If T is surjective, this will happen. So this is the first thing we need to tell. Now there is another thing about there is a relation between T is injective and kernel of T. Do you know what that is? When T is injective, what can we talk about the kernel?
Nullity is 0.
Exactly.
Zero.
So kernel is basically zero vector space. Right? So this is again an if and only if. So this gives nullity is 0. Correct? So another important thing we know that if nullity of T is 0, if and only if T is injective. So these two are really important. So the mapping which I have given, is this an injective linear transformation?
Yes.
No, sir.
Yes.
No, sir. No, sir. It's not injective.
Not injective, right? Because all these vectors x, x, x are going to the same vector 0. So it cannot be 1 to 1, right?
Yes. Right.
All these vectors. So it will only be injective if only 0 vector is going to 0. Because 0 vector will always go to 0. And no other vector is going to 0 for T to be injective. Clear?
Yes, sir.
Anyone has any doubt till this point?
No, sir.
Anyone has any doubt? No, right? Okay, great. Now, if I use the Rank-Nighty theorem a little bit, we know this is the case, right? T is from V to W. Let's see what other things we can come up with. Right? If T is injective, then nullity is 0. Then rank of T must be same as dimension of V. Right?
Yes, it will be full rank.
It will be full rank. Correct. Full rank means it is not full rank.
Yeah, it will
Rank
be
of
exactly equal to whatever dimension we have for V.
For V, not for W. Huh?
Yeah, what for V?
Yeah. And if T is surjective, what we can talk about? Surjective means rank T is same as dimension of W. Right? So dimension of W plus nullity of T is dimension of V. Now there is something called bijective. Bijective means what?
It is both injective and surjective.
Both injective and surjective. So that means nullity is 0, correct? As T is injective, and rank of T is
Rank of
dimension of W, right? In that case,
Dimension of W will be
W
dimension
will
of
be
B.
equal to dimension of V.
so if you have any linear transformation from Rn to Rm, it can be bijective if and only if m equal to n. Otherwise, it cannot be. Right? It is not necessary if we have a transformation from Rn to Rm, then it must be bijective. I am not saying that. I am saying it cannot be bijective if m not equal to n. Right? If I am giving you a linear transformation like this, R3 to R2, then whatever linear transformation I give here, it cannot be bijective. Correct?
But
Yes.
sir, in an activity assignment, there was a question where it was mapping from R3 to R2 transformation, and we got that isomorphism.
No, you cannot get. If you got
Answer
it,
was also
no,
showing
you
correct.
cannot get. You will check again. It is not that.
So can I say, sir, in that question, that was a subspace of R3.
That is what I am saying. You cannot get like this, right? Because we have shown this, right? If it has to be bijective, then the dimension of both the domain and codomain must be equal, right? Otherwise, cannot be bijective. But I am not claiming that if it is from R2 to R2, then all the linear transformation is injective. It is not the case. I can take this example of all the vectors are going to 0. This is the map from R2 to R2, right?
Yes, sir.
Is it injective?
No.
It is not injective. Is it surjective? Is it surjective?
Yes.
Not
No.
surjective.
No.
Not
No.
No, sir.
Not surjective.
What is the image? Image is the zero space only, right? Zero
Sir, it
vector
only
space.
zero.
Yes.
It is
And
only for
codomain
zero.
is R2.
What is
Range
nullity of it?
is
What is nullity of T?
Sir, 2.
2. What is rank of it?
0, sir.
Zero.
Yeah. So rank night theorem also satisfies. Rank plus nullity is 2. Right? Okay. What is the null space? Can you tell me? Null space.
0,
Entire R2.
0, comma
Sir,
0.
entire XY, sir. R2, sir. Yes, sir.
Entire R2.
Okay.
It will
So
come to
yeah, this is what I wanted to say. So this is one thing we can derive from rank nighty theorem.
Sir,
Now let's come to
Sir, so before you go
What
on,
is null space? Can you
can
explain?
you just clarify how null space became R2?
Yes, sir.
all the vectors are going to 0.
zero.
All the vectors of R2 are going to 0.
Oh, in this case, sir.
Yes.
Okay. I thought
Sir-
it's generic.
Sir, is it possible
can
to
be generic, sir.
visualize transformations anyway?
Huh?
Sir, is it possible to visualize transformations anyway geometrically?
I think you asked this in earlier live session also, right?
Yeah, no, sir. It's first time I'm joining any live session.
Oh, so in one live session I have shown it. Okay. So basically, what I mean, suppose I have this R3. Okay. This is R3, and here suppose I have R2. Maybe.
Yes, sir.
So I will define a map from R3 to R2. Suppose I am defining a map like this. T, X, Y, Z is going to, let's take a easy map. X, Y, 0. Okay. So what I am getting here? So take any point here, X, Y, Z, any point. Where it is going? It is going to X, Y. So basically it will be some point here, X, Y. So this plane will come as my R2 here, right?
Okay, sir.
Here the coordinate on XY plane is basically XY 0, right? But here what I am writing as X, Y, right?
Yes, sir.
Yeah. So this plane is a subspace of R3, but I am representing it in terms of R2. So this is how linear
transformation. Sir, using decimal complicated transformations are there. So
you can play around GeoGebra and all this. Yeah, you can see this type of linear transform, but it is difficult to visualize in GeoGebra or Desmos because you can consider either R3 or R2 in the place. You cannot get these two together, right? So it will be difficult. You have to visualize it in one space itself. So it will be more difficult. I can draw it.
I saw some videos, sir. In those videos, sir, they were showing everything like, sir, what kernel is, sir, it does not transform and other points get shifted somewhere. So geometrically, it was a bit more intriguing.
Right. But all things will be inside one diagram, right? Because
yes, sir. Yes, sir.
I mean, the domain and codomain will be your same thing in that case. Otherwise, you cannot visualize.
Yes.
Yeah.
Okay, sir.
Okay, I will. So this is one thing. What I was going. Anyone has any doubt in this point? What we have discussed till now? Rank nullity theorem. What is null space? What is n space? What is rank and nullity? Anyone has any doubt?
No, sir.
Sure. Tell me what is the null space of this? Null space of T in this example.
So 0, 0, 0.
So 0, 0, Z.
0, 0, Z.
0, 0, Z, right?
Yes, 0, 0, Z.
So what is nullity of this?
1, sir.
1.
What is rank of this?
2.
2, sir.
And is T subjective?
Yes, sir.
It is subjective, right?
Yes, sir. It's
Yes, sir.
Because dimension of R2 is 2 and dimension of the range space is also 2. It is same as that. So it is a subjective. But is T injective?
Sir?
no, sir. No.
No, sir.
Yeah. So I think this portion is at least clear. Now there is one important concept which was a matrix representation of a linear transformation. Right? So what we are doing here? Suppose I am taking R3 to R2. Take a map like this: x, y, z. 3x plus 5y.
From
4x plus 3z. Suppose this is the transformation item. Now, suppose I am considering, so when I am talking about matrix representation of a linear transformation, I need to know what are the bases for both the domain and codomain. I need to know, otherwise I cannot do that. So suppose to begin with, I am starting with the standard order basis for both R3 and R2.
Sir, 1 minute.
Yeah.
I have a query. Here earlier you wrote some matrix like 3, 5, minus 9, 4, 3. 403. Then what was that? Was it not T's
Ah,
representation?
You will get the answer in 2 minutes. Okay? You will get the answer in 2 minutes. What was that matrix? Okay? So, you know how to write the matrix representation of it. What is, you need to get the image of these vectors. Beta is the basis of this domain and gamma is the basis of codomain. So what is T100? Can someone tell me?
3.
Just
3,
3.
3.
3, 4.
4, comma.
What is 010?
5,
5,
0.
5,
0.
0.
5, 0.
What is 001?
Minus
Minus
9, comma
Minus
3.
9, 3. 3.
If I want to express it, so this is a vector in R2, so I must express it in terms of these two vector, the basis vector. I can do it. So if I do it, what I will get? I will
Plus
get
4
like this.
into 0, comma 1. Yes.
This is what I get here, and this is what I get here. Correct?
Yes, sir.
Yes, sir.
Yes, sir.
Now, if I, so the matrix representation with respect to these two basis vector, beta and gamma. The matrix representation is basically, I should write it in terms of column. 3, 4, 5, 0, minus 9, 3. Right? Now you get the answer. What the matrix A I was writing earlier. This is this matrix, no? 3, 5, minus 9, 4, 0, 3. This is the matrix I was writing earlier. No?
Sir, so both are same?
Yeah, both are same. Okay. So remember the matrix which I was writing earlier when I was writing TV equal to AV. This A is basically the matrix representation of the linear transformation with respect to standard order basis, not other order basis. The standard order basis is really important here. Okay.
Yes, sir.
So the matrix I was writing earlier, that is nothing but the matrix representation. So this was my A earlier. The matrix representation with respect to standard order basis. Okay. And for that, only for that, the standard order basis, the null space of the matrix and the null space of the linear transformation will be same. It will not true for any other matrix representation.
So, sir, we will get
other than standard order.
we will get another transformation if we change the basis.
Another matrix representation will get. Transformation is fixed.
Okay, okay. We'll get
Right?
the
For a
same.
transformation, we are getting different.
Okay, 3x plus 5y minus 9z.
This is
We'll
given.
get,
This is fixed.
that same.
This is fixed.
Okay, okay.
For different basis, we will get different linear transformation. This
Okay,
A,
sir.
the A I was mentioning earlier, that particular matrix I will get only when I will consider standard order basis for both domain and codomain. If I change any order basis, any basis for the domain and codomain, any one of that even, if I change, I will get different matrix, and for that null space will be different. Null space of the matrix and null space of the transformation will be different. That is what Susmita was telling at that point. Okay?
So, sir, but nullity will be same.
Nullity will be same. Nullity, rank, all will be same, but null space will be different. I will give example.
Okay.
Right.
So, sir, null space and what about image space?
All will be different.
Okay.
That is the case. But rank and nullity will be same.
Sir.
Okay?
Okay.
Okay.
Sir,
So,
null space will always be with reference to standard order basis, is it? Whatever null space we add, that will be with reference to standard order basis, no?
I am not getting your last part of the question. What you were saying?
So when we say null space and the matrix transformation will take based on the basis what we take. So whether null space what we get is always with reference to standard order basis?
With respect to?
Standard ordered basis?
No, null space of a linear transformation, what I am saying is null space of this matrix. Okay, so matrix we are getting with respect to standard order basis. Now the null space is a space. It does not depend on the order basis or anything. I am saying the null space will be same for the linear transformation and the matrix only when we are considering standard order basis for both domain and codomain. That is what I
got
am
it.
saying.
Got it. Got it.
Okay. So if I take the same linear transformation, okay, 3x plus 5y minus 9z. So let me write it here again. 3x plus 5y minus 9z and 4x plus 3z. Okay. If I have this, if I change the first, let's see that whether basis changes. Suppose I take these bases as 1, 0, 1, 0, 1, 1. What was another 1, 1, 0? If I take this one, and if I take gamma, say gamma is same, standard one. Okay. Will the matrix be different? Let's see. What is T101? What is T101?
Minus 6,
Minus 6.
7.
Minus 6 and 6, comma 7.
Minus 6 and this is 7. Correct. T of 0, 1, 1.
Minus 4, comma
Minus
3.
4.
Minus 4, comma 3.
Minus 4,
Comma 0. Oh, sorry. 3.
3.
Yeah.
3.
Sir, have you changed beta means basis for domain?
Huh?
You have changed basis for domain?
Yeah, I have changed basis for domain, but does not change the basis of codomain. Okay. And I am seeing whether the matrix changes. What is 1, 1, 0?
8, comma 4.
8, comma 4.
So what is the beta prime gamma? So this I can again write as 1, 0, 7, 0, 1, minus 4, 1, 0, 3, 0, 1, 8, 1, 0, 4, 0, 1. Right? So I can get minus 6, 7, minus 4, 3, 8, 4. So you can see the matrix is changed, right? The earlier matrix and this matrix is changed. So clearly null space will change, right? For this matrix.
Yes, sir.
Because those two are different matrices. So null space may change. Maybe they are same, but there is a possibility that they may change. So if I want to find the matrix null space of a linear transformation, if I want to go via some matrix, I always remember that I should work with the matrix of standard order basis. Okay. Only in that case, the null space of linear transformation and the null space of the matrix will be same. Otherwise, it may not be same. Okay.
Okay, sir.
Okay. Fine. Suppose, so let's consider one example in R3 to R3. I will stop with this example. So T with x, y, z. This is x minus y, y minus z, z minus x. Let's take this one. Okay. So before going to the matrix, can someone tell me what is the null space of this?
1, comma 0, 0.
Sir, x, y, z.
Beta or gamma, sir?
No, I am saying what is the null space of T?
Sir, all x, y, z.
Yeah.
All x, y, z.
No,
Everything is going to 0, you are saying.
This is x, y, z such that x equal to y.
Sir, x equal to y equal to z.
Correct. So basically, yeah. If I write definition, I will get the equation like this. So basically, three equations I am getting: x minus y equal to 0, y minus z equal to 0, and minus x plus z equal to 0. These three equations. So the system I am getting is 1 minus 1 0, 0 1 minus 1, minus 1 0 1. Right?
Yes, sir.
R3 plus R1. If I do, what I am getting? 0 minus 1 1. Right? And again, if I do R3 plus R2, 1 minus 1 0, 0 1 minus 1, 0 0 0. This last one is lost. Then what about this one? R1 plus R2. I can do 1 0 minus 1 0, 1, minus 1, 0, 0, 0. Right? So the null space I am getting is x minus z equal to 0, y minus z equal to 0. So x equal to z and y equal to z. Right? So the null space of T is basically x, x, x. Right? Clear?
Yes.
So what is the nullity of this matrix?
1, sir.
1.
Great. Great. Okay. Now I have started with this linear transformation, right? X minus y, y minus z, z minus x. What is the matrix representation with respect to standard order basis? Beta, gamma, both are the same because this is R3 to R3. So I am taking the standard order basis for both the cases, domain and codomain. Can someone tell me what that is? So T of 1, 0, 0 is?
Sir, 1, 0, 0.
0 minus
0
1.
minus 1.
Minus 1. T of 0, 1, 0 means?
Minus
Sir,
1.
minus 1.
1. Right. What is this one?
0.
Minus 1, 1. 0 minus 1, 1.
1.
If I express this in terms of the standard order basis again, I am getting this, right? Okay, now this one is this. So I am writing as a linear combination of these three. Basically, the same thing will come. Okay. So if I write it as column, I will get T beta gamma. So this is 1, 0, minus 1, minus 1. What I have done here?
Sir, 1, 0 minus 1 will be written like this now.
I have done some mistake, no?
Not down. Sir, it will be written in column
Sorry,
wise, no?
So it will be column wise 1, 0, and minus.
1, 0, minus 1.
Minus
Then
1,
the
1.
second column will be
Minus 1.
Minus 1, 1, minus 1, 1.
0
0, minus 1, and 1.
Correct. So this is the matrix with matrix representation with respect to standard order basis. And if you see, when I was finding the null space of the matrix, I was using the same matrix,
Same matrix.
right? So
Yes.
these two matrices are same. So null space of this matrix, null space of this matrix. So beta gamma, remember it was standard, the same as null space of T. As a space, they are same. Nullity is obviously same. So nullity of this matrix is same as nullity of this. Rank of this matrix is same as rank of T. Yeah.
Yes, sir.
Now the interesting point is, suppose for this linear transformation, the same linear transformation, x minus y, y minus z, z minus x. I am changing the order basis. So I am taking this. Now this is not standard one, right? I am taking gamma also in this fashion. Can you tell me what is the linear transformation now? Can you just work with me? So what is T of 1, 1, 0?
0,
0, 1, and minus 1.
What is this one? 0, 1, 1.
Minus 1.
Minus 1, 1, 0. Minus 1, 0, 1.
Correct?
Yes, sir. Yes, sir.
What is
Yes,
this one?
sir.
1, 0, 1?
1 minus
1
1 minus 1, 0.
0.
0.
Now I can I express this as the linear combination of these three, what I will get? I want to express this one as a linear combination of these three. Now it will be little bit difficult, right? Yeah.
0 into 110.
0, 1, 1, 0. Then?
So why to use
it? It is not so
So if
simple.
we are using 0, then why should we use that?
So it is somewhat different.
No, what you are saying, if we use 0, then why you should use this?
Sir, because that will not add up anything.
But it should come as an element of the matrix.
Yes, sir, but right, it will come, but sir, we can escape it.
No, we cannot escape that. It will be an element of the matrix, right?
Yes, it will be used.
Yeah.
Sir.
So basically, if I want to write it, I should write as this. So I should find A, B, and C like this, right? So what is this? This is basically A plus
A will be
C.
1, A will be 1, B will be 0, and C will be 1.
Oh, A plus C, comma?
C will be minus 1. C will be minus 1, sir.
Okay, let me see. So A plus C is basically 0. A plus B is 1. And B plus C.
B plus C equal to
minus 1. Right? So this is. And what is the solution you are saying? A is
Sir,
1.
A is 1, B is
B
0,
is 0,
C is
C
minus
is
1.
minus 1. Exactly. So this is solution we get. So this is 1. So basically you have to solve this equation and then you will get this 0 and minus 1. This is minus
Sir,
1.
we'll always get only unique solution. I mean,
It
unique.
will get a unique solution because these are linearly independent.
Oh, okay, okay.
Right? So the matrix, coefficient matrix will form by this will be invertible because these are linearly independent, right? You have learned this in week 4, week 3, week 4. Right?
Yes, sir.
Linear
Yes.
dependence.
Okay.
Yeah. So this is the same thing. Okay, what about this one? Now in this case, A plus C should be minus 1, A plus B should be 0, and B plus C should be 1. Now can someone tell me what is the solution? Same
minus 1, 1,
thing,
0.
same type of thing. Huh?
Yes.
Minus 1, 1, 0.
B is
Minus
equal to
1.
1, C is equal to
1,
0.
0.
Great. Now what about the last one?
0 minus 1.
Huh? So in this case,
0
A plus C
0 minus 1.
0, minus 1, and 1.
0. This is minus 1 and 1. Right?
1. Yes.
So we get a linear combination of all our images. Now we can write the matrix. Right? The matrix now we are getting. So let me call it beta prime and gamma prime. So beta prime, gamma prime is basically 1, 0, minus 1, minus 1, 1, 0, 0, minus 1, 1. So see, this is not the same as the earlier matrix, right? Or is it same? You get the same matrix.
It looks like same.
It looks like the same. So
Yes, sir, it's the same
I have
matrix.
chosen a very wrong basis for it. Okay, so let me see. So for this case, it finally came. Suppose we take this beta prime as what I have chosen. This one and gamma. Let's take standard order basis.
I think it is a linear equation. Means it is in form of plane equation, so it is minus.
No. It should not be. I mean, it may be different in some cases. So in this situation, it came as same, but it should not be always, right? So if I take this beta prime as by the new order basis, and gamma as my standard one, right? Now can I say something about the matrix I am getting? Now can you tell me what is the matrix? So images will be same, right? T1, 1, 0. We know the image 0, 1, minus 1. T0, 1, 1. The same as minus 1, 0, 1. And T0, 1, 0, 1. The same as 1, minus 1, 0. Now what is this? T
Matrix will be column wise 0, 1, minus 1.
0, 1,
0, 1, minus 1, minus 1, 0, 1, 1, minus 1, 0.
So now I am getting this matrix, right? So this is the not the same matrix as the earlier.
Yes, sir.
Right? This is not the same matrix as the earlier. The earlier matrix 1, minus 1, 0. Now I am getting a different matrix 0, minus 1, 1 like this. Right? So basically for different ordered basis I am getting different matrices, and it is not necessary that we will get to the same null space because the matrix is changing, right? So for different matrix the null space may vary, maybe same but maybe varied also, right? So the null space of a linear transformation only matches with only the null space of the standard order basis. That is the point I was trying to make. Is it clear? But in all the cases nullity and rank will be same. Whatever basis you choose and you write the linear the matrix representation in whatever matrix whatever basis you choose, the rank and nullity will be same. That cannot be different. That is always same. But as a space, the null space and the range space, they may be different for different order basis. But for standard order basis, it will be same. Okay? Is it clear?
Okay, sir. Yes, sir.
Yeah.
Okay. Okay. So this is basically what we had in this week 5 and 6. And this is how these are related. Okay? Anyone has any doubt? Now, will you be able to solve problems? Or still not confident enough?
No, we'll be able to solve. We'll be able.
We'll try, right? Now you
Yeah,
can
yeah.
try solving problem. Anyone has any doubt, you can ask me for week 5 and 6.
Sir, there is one question wherein it is asked about trace. So I'm not able to recollect what is the meaning of trace.
Trace means sum of diagonal.
Okay.
Sum of diagonal.
Fine.
If the basis other than standard basis, we how we find the basis for image space and basis for null space.
So one way is basically you trace back to your original transformation. What is your transformation? Right? And from there you directly find the null space and range space. So suppose I am giving you, nice. This I should do somewhere. Good that if you ask this. So let's see. I am having a map from R2 to R2. Okay. And with respect to this ordered basis, which is not standard as you can see, say 0, 1 and 1. Okay, this is the ordered basis I am getting, and the matrix representation with respect to this ordered basis, it is given like say identity matrix. Okay, this one. Can you get back the linear transformation from here? What is the linear transformation explicitly? How we can get back, right? So basically what it is given here, you know how we write this matrix representation, right? So T of 1, 1 is basically what is
1,
this is 1 into 0, 1 plus 0 into 1, 1, right? Because then only we will write this as a column. Correct? And T of 1, 0, what is this? This is 0 into 0, 1 plus 1 into 1, 1. Correct?
Yes, sir.
Is this clear? Because this 0 is coming here, this 1 is coming here. Right? That's how we write matrix representation. So we know the image of 1, 1. What is this? 0, 1. We know the image of 1, 0. What is this?
1.
Okay. So we know this thing. Now we want to find the image of xy. Right? That is what we have to find. T of xy. What is that? Now earlier we have done it, right? How we can express it. So basically we have to express this in terms of these two, because we know the image of these two elements. We know the image of basis element. So we know what the linear transformation is. So basically I should write it as a linear combination of these two elements. What is my AB? So A plus B, and this is A. So A plus B is X and A is Y. So B is basically X minus Y. So XY is nothing but Y 1, 1 plus X minus Y 1, 0. Correct? So T of XY is Y T of 1, 1 plus X minus Y T of 1, 0. Now what is T of 1, 1? It is 0, 1. And what is T of 1, 0? It is 1, 1. So what I am getting? 0, Y plus X minus Y, X minus Y. So this is X minus Y, and this is X minus Y plus Y, this is X. So this is the mapping, original mapping. Now you can find out the null space and brain space, whatever you need.
So this is from matrix, so we are going from reverse process.
This is from matrix, we are going to the explicit definition. Right? Now suppose, this, for this one. What is the null space? Can someone tell me the null space of it? Null space of T?
Sir,
X
is the null space of
Y.
This is 0. X equal to Y and X equal to 0. So X and Y both are 0, right? So this is 0, 0. This is the null space. Right? What is the matrix representation with respect to standard order basis? Standard one.
1.
Yeah. So T of 1, 0 is what? 1, 1. And T of 0, 1 is? What is this? Minus 1,
Minus 1, 0.
So it is 1, 1, minus 1, 0. This one. Yeah. So see, your matrix has changed. Earlier it is this, now it is this. Okay? Clear?
Okay.
Yes.
Okay, great. So you understood, if I have given a matrix, I can trace back to the original linear transform. And then I can solve for null space and range space, right? Got it?
Yes, sir.
yes, sir.
Okay. Any other doubt you have? So mainly these type of questions are there. So let me do one more type of problem. So here we are doing for Rn to Rn, but suppose I have a mapping from M to A to M to A, M to R. Right. T of A as P of A, where P is some matrix, say 1, 0, and 1. Now, suppose M to R, in case of M to R, I have, so you know what M to R is, right?
2 by 2 matrix.
Someone tell me?
2 by 2.
2 cross 2 matrix. Can someone give me standard order basis for this one?
1, 0, 0, 1.
No. 2 cross 2 matrix, no?
Hmm.
So 4
0,
elements.
1, 0, 0.
4 elements should
0,
be
0, 1,
0,
0.
0, 1, 0, 0, 0, 0, 1.
there. This 4 elements should be there. So I am taking this as beta and gamma, right? And I want to find the this matrix representation of this linear transformation, P into A. Right? P is this matrix. So what basically I am doing? So I need to find the image of this one first. 1, 0, 0, 0. P is this matrix. 1, 0, 1, 1. This is my A. 1, 0, 0, 0. So if I do the product, what I will get? 1. This is 0. This is 1. This is 0, right? What is this matrix?
Sir, here what is A? This the elementary consideration.
A is basically the vector we are taking from this M2R.
The basis vector.
It's not basis vector here. So in this case, this is one of the basis vector, but in general, A is basically any matrix of M2R, any 2 cross 2 matrix. So the transformation is defined like this. So how we can define a transformation? So I have to take a vector from here, right? M2R. Now any vector of M2R basically a 2 cross 2 matrix. So I have taken a 2 cross 2 matrix, and the transformation is defined like P into A. P is a fixed matrix. I have taken a product of the vector with that matrix. Right? So this is a 2 cross 2 matrix, this is a 2 cross 2 matrix, I will get a 2 cross 2 matrix. So the image will lie on in 2 cross 2 matrices. Is it clear?
Yes.
Yes.
Now what is the second one? What is the image of this?
1, 1, 0, 0.
Okay. No, first one is 0, no?
0,
Ah.
1,
Yeah.
0, 1.
0, 1. What about the third one?
Zero, 0, 1, 0.
What about the fourth one? Yeah, what about the fourth one?
0, 0, 0, 1.
0, 0, 0, 1.
So this is 0, this is 0. Now I have to write these 4 matrices as a linear combination of these 4 matrices, right? So if I write first one as the linear combination of these 4 matrices, let me call it E1, E2, E3, E4. What is the combination I am getting? 1 E1
Plus 0 E2
0
plus
E2
plus
1
1
E3
E3 plus 0 E4.
What about the second one?
0, E1.
0 E1 plus 1 E2 plus 0 E3 plus 1 E4.
Right. Third one?
0
0,
E1
E1
0, E2.
plus
0
0, E2
plus 1 E3
plus 1, E3, 0, E4.
0
What about the
E1
fourth
0
one?
0, E1, 0, E2, 0, E3, 1, E4.
Okay. So the matrix representation of T with respect to this standard basis here is what? It is 1 0 1 0 0 1 0 1 0 0 1 0 0 0 0 1. This 4 plus 4 matrix will be the matrix representation. Is it clear?
Yes, sir.
So this is one special type of linear transformation you can come across. Right? Understood? Basically, we are doing the same thing, just more calculation is involved, nothing else.
Yes, sir.
Okay? So I think there is one graded assignment with this slide. So the main point to take away from this session is basically that we can relate the null space of a matrix with null space of a linear transformation. But those two spaces will be equal only when we are in standard order basis scenario. Basically, the matrix representation with respect to standard order basis. If we do that, the matrix we get, the null space of that matrix will be same as null space of the linear transformation. Otherwise, it may not be same. It may be same, may be different, but it does not guarantee that the null space will exactly be same. But nullity and rank will always be same. So if you know the matrix representation with respect to some vector, some basis vector, right? And if you can calculate the nullity and rank of the matrix, then you know the nullity and rank of the linear transformation. But you don't know precisely what the null space is or the range space is. That precise null space and range space you know only when you are dealing with standard order basis. Is it clear? This is really important what I am mentioning. Okay. And you know how to find null space, you know how to find range space now. And rank-nulity theorem is giving you a power to do that. Just finding nullity, you can now know what is your rank, right? Because it's enough to find the nullity. Using rank-nulity theorem, you can find the rank also, right? And now you can conclude when a linear transformation is bijective, when it is not. Clear?
Yes, sir.
Anyone has any doubt?
Yes, sir.
Okay.
Great. Any doubt
No, sir.
in week 5 and 6? This 5 and 6 is really crucial. I know it is little bit of abstract science, but it is not very.
Sir, can you please repeat how to check onto-ness?
Onto-ness, basically, for onto, you have to check what is the rank of the linear transformation, right? Now, if rank of the linear transformation is same as the dimension of the codomain, then it is linear onto. Suppose T is from V to W, say in general I am talking about V to W. You know how to calculate the rank, right?
Yes, sir.
If rank of T is same as codomain of W, sorry, codomain, dimension of the codomain, that means dimension of W. Then T is onto. Yeah.
Yes, sir.
Suppose you have a linear transformation from R2 to R3. Okay. Tell me, can it be onto? I am asking this to everyone.
No, it cannot.
No,
Why?
sir, it cannot be
No.
onto.
Why?
Domain is lesser than codomain.
Yes, sir.
Because
So basically, if I
Sir,
write
because R2 to R3, so dimension of R2 is 2 and 3 is 3, so it's not possible.
right,
Everyone will not have a pre-image.
right. So
Because the
basically,
maximum rank it can have is 2.
exactly, correct. So from rank-nulity theorem, what I am getting, rank plus nullity is here 2. So maximum rank it can have is 2, right? It cannot have more than 2. If its rank is 3, suppose it is on 2, its rank is 3, then nullity is -1, which does not make any sense, which is absurd, right? The least nullity is possible is 0, the 0 subspace, correct? So rank cannot be more than 2 in this case, so it cannot be on 2. Clear?
For onto,
Yes,
we have
sir.
to check codomain.
Right,
When you-
rank of T should be equal to rank of the codomain, correct? But here it cannot happen, right? Because dimension of codomain is 3. Rank can never be 3 because rank should always be less than 2 in this case. Clear?
Yes.
So
Yes,
if
sir.
T are n to Rm, I have this. Then if n is strictly less than m, then T cannot be on. Clear?
Yes.
Clear?
Yeah. Yes.
Okay. Now similar question I can ask. R3 to R2. Can T be 1 to 1?
No, sir.
Can you give me why not?
Because, sir, the minimum nullity is 1 here.
So why?
Maximum rank is 2.
Rank plus nullity will be 3.
Right.
And rank of T cannot be more than 2.
Because rank of T cannot exceed the dimension of the codomain, right? Because
Yes.
range is always inside the codomain. This is my range. This is my codomain. And the range space should sit inside that. It can cover the whole thing, or it should sit inside that. So it cannot be more than the dimension of the codomain. So rank T must be less than equal to 2.
Less than equal to 2. Correct.
Less than equal to 2. So now it must be greater than equal to 1. Right? It cannot be 0. Because if nullity is 0, then rank is 3, which is not possible. Rank 3 is not possible here because dimension of the codomain is 2. Rank should be less than that. So here also the answer is no. Clear?
Yes, sir.
Basically
Yes,
some
sir.
application of rank nullity theorem. Right? These are some application of rank nullity theorem. Okay? Understood?
Yes, sir.
Yes, sir.
Okay, great. So this is basically more or less complete.
Sir, please upload this PDF, sir.
Yeah, I will upload it. I will.
Okay, sir.
Yeah, sir. Yesterday sessions PDF not uploaded.
I will upload it right now. Yesterday's also today's PDF I will upload both of them.
Sir, can we get the recording of this session?
Yeah, I have recorded it, but I will upload it tomorrow because it will take some time to process. So tomorrow you will get the link.
Okay, sir.
Okay. So I think week 5 and 6, more or less, you have some idea now, right?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Oh,
sir.
great.
Yes.
Okay.
Sir, can I ask doubt from activity?
Yeah, you can.
Sir, it's 5.5 question 9.
5.5. So I have given a form in the chat, so those who are present now, you can fill this. I think many of you have left already, but still. Yeah, 5.5.
Yes.
Activity.
Yes. Question 9.
What is the doubt?
I don't even understand the question. What is 9?
Which one?
9.
You have not understood this question.
Yes.
Until now.
No, means.
After this discussion also.
So means here V is X and Y means R2 to R2 and matrix. Then means how, what is this? No sir, I don't understand this question.
Till now, is it?
No sir.
Because I have mentioned this, this is what I have begun with the discussion. Right? So if you see, I have started with this writing TV equal to AV. I have mentioned what A is in every case, how you are getting it.
Okay sir, I will try.
So basically here, what you have to do. So if you know what is your rank and nullity for this matrix itself, you know the rank and nullity of T, right? That is what I have said. Right?
Yes.
You don't have to write down the whole linear transformation. You can, even it is quite clear. 3,2 into xy, right? This is, so let me give you a little bit hint, but you should do it now. Right? So 3,2 and 4,5, right? Is this the thing? 3,2, 4,5, right? This is your A. Your V is xy, and Txy is TV is AV. This is what it is written. Correct? So T of xy is basically 3, 2, 4, 5 xy. So what you are getting 3x plus 2y, comma 4x plus 5y. This is your linear transformation. Okay. But we really don't need to go till this point. You know this matrix, right? Do you know what is the nullity of it, of this matrix? What is the nullity of this matrix? Do you know that?
3x plus 2y is equal to 0. And
We really don't need that, right? For finding the nullity of it. How we find the nullity of null space of matrix A? By doing row reduction, right?
yes.
So row echelon reduction.
Basically, what you are saying is correct. 3x plus 2y equal to 0, 4x plus 5y equal to 0. But that eventually will give us this coefficient matrix, right? To solve this.
Yes.
So basically, we have to do row reduction of this one.
Okay.
So if you do row reduction, so 3, 2, 4, 5, basically, okay, let's do row reduction, but we don't need that actually. So 1, 2 by 3, 4, 5. So basically this is R1 by 3. Now what we should do? R2 minus 4R1, correct? 1, 2 by 3, 0, 5 minus 8 by 3. So what I am getting? 1, 2 by 3, 0, 15, 7 by 3. Right?
Yes.
3 by 7 are 2. 1, 2 by 3, 0, 1. So R1 minus 2 by 3 R2 will get 1, 0, 0, 1. So what is your null space? Can you tell me? Null space of A?
0 vector.
0, 0.
0 vector.
Correct, because this is x and y. So x is 0 and y is also 0, right? If I write x, y, from the first row I am getting x equal to 0, from the second row I am getting y equal to 0. So this is 0 vector. So nullity is 0, right?
Yes.
Are you-
Yes, yes.
So nullity is 0, is it clear? I mean, we don't have to do that because if you know, calculate the determinant. What is the determinant? 15 minus 8, 7. So determinant A is non-zero. Correct? So A is invertible. So this system of linear equation has a unique solution. And that solution is 0, 0, right?
Yes.
Correct. So the solution is 0, 0 means that is unique. So null space is nothing but the 0 vector. 0, 0. So null space is 0, only the 0 subspace. So nullity is 0. Nullity is 0 means, what about rank nullity theorem? And this nullity is same as nullity of T. And this null space is same as null space of T. And what about the rank?
2
rank is
minus
2.
2. So rank will be 2. Now T was from 2 to R2 to R2. Nullity is 0. That means T is, when nullity is 0?
T is
1 to
isomorphic.
1.
1, 1 and on to both.
So here rank is also 2. So T is on 2, right? Because
On
rank is matching with the dimension of the codomain.
Dimension of codomain.
So T
Yes.
is both 1 to 1 and on 2. So T is
Okay.
isomorphic.
Isomorphic.
Yeah.
Yes.
You should do that, right? Because there is nothing I have done which I have not stated in the lecture. Okay?
Okay.
Sir, one request. Is it possible to, replace those lectures of Sarang sir with the lectures of your team? Because
So you are saying Saransa's lecture is not conceptually well, is it?
yes, sir.
Which is not the case. I assure you.
Sir,
It is not the
he is using many technical jargons and math concepts are not so clear from his lectures
No, if
unless
you-
I attend the live sessions.
Because it should, I mean, you see that all the topics should be covered in 2.5 hours, right? In a week. for a lecture. So he has to keep something, some calculation beforehand. He has to use some techniques beforehand, right? And
That
that's
is
why
not
we
the
are.
issue, sir.
Yeah.
Issue lies in basic concepts. Means
No,
he is
all
not
the
backing
basic.
it enough with examples like you did today.
So
You
that
explained it
that
in
is
a
what I
very
am saying.
detailed.
All the example he cannot do in a lecture. That's why other tutorials and all these live sessions are. Right, and for that we have created the solve with us assignment, all the activity question. I mean, only the lecture video is not the total week content. It is a part of the content.
Actually,
right? So that's why all this suppository material should come.
Sir, what I mean to say is lecture video are not acting as a guidance to solve the questions at least.
It may not be.
Yeah,
Right.
that
is
is
the
the
case.
problem because in
But
early
that's why that is what I am saying. Only seeing by the lecture video will never be enough for any of this type of course, which covers a huge number of concepts. A lecture video cannot be enough. Otherwise, it should have been a 6 or 7 hour lecture video. How we treat in this live session, if Sarang sir have taken all the example, clearing all the doubts one by one, then it may have gone up to 7 or 8 hour lecture video.
It's not feasible.
Right? Because that is not feasible. Because in weekly we are taking 3 live sessions, right? And all these are nearly 2.5 hours to 3 hours. So you can see that, assuming some concept of the earlier week, it comes up till 8 hour or 9 hour video, which is not good for a lecture video, right? So for Sarang sir, lecture video is not an issue. Conceptually, it's not problematic. It is very clear on the concept, but you need some suppository material, that I agree. And that what we provide in other contexts, right? The book is there, the live sessions are there, the solve with us assignments are there. Whatever content you like, you can choose that path, right? If you like live session, you come to live session. We are happy to teach. If you want to go to the book, you go via book.
Yes,
The book is already we have
book
uploaded
is,
in the.
I have read it. It is the compilation summary of everything.
Yeah. And in some
Sir,
portion
but
you will get more than the summary.
Sir, but the thing is this, ki when we watch the lecture video, we ends up like we don't understand anything, and even if you teach this concept, this become clear, but from the lecture video, we become hopeless, or we are not getting anything.
Because there is a difference. You can ask me when you are stuck at some point, but in lecture video you cannot do that.
But sir,
Right?
there are so many technical terms. This go way over our heads.
Really?
Yes, sir. The lecture
Yes.
videos are very much of higher level.
No, it is not of higher level. It is what I feel is basically.
See.
Yeah, Sushmita, go ahead. I need some.
Sir, actually,
exactly
the
what
issue
Sushmita has
it is
told.
not with the other lecture videos are also there of other subjects. They are covering the core concepts and examples are covered in tutorials and a live session. So that the lecture video is not acting as a guidance for to solve examples. That is what the issue is.
Yeah, Sushmita, you were
Sir,
saying something.
actually, till week 4, till week 5, it was okay. But week 6 jumped to some other level. That's why we are facing the main problem. Because till week 5, it was okay. It was understandable. But from week 6, it is.
Because from week 6 or even for some student, it is from week 3 itself. The concept is little bit in abstract sense, right? For different student, I know it will be different because we cannot process everything in same level, right? For me, some concept may be very difficult to gauge, and for someone it may be very easy. So it is always there, right? Sushmita, were you saying something?
Yeah, this only. So in the live session, we wait till you understand something and then we proceed to the next topic. But in the lecture video, you cannot expect that, right? You're not present when the lecture video is being taken. So you cannot get your doubts clarified. So you have to stop where you don't understand and go back and start watching it again till you understand. But here, since you ask us and we out, it takes lesser time compared to you watching the video again or things like that. That's why it feels that live sessions are so much better, but that's not the case. The lecture videos are beautiful actually. Once you understand all that